Renato. Esse Daniel.
Ô, Daniel, tudo bem, cara?
Você tem um pendrive? Eu consigo passar atualizar o...
Ah, você quer atualizar? Eu não tenho pendrive, não.
Só se tiver. Então, deixa.
Você consegue fazer upload dela no...
Eu vou tentar logar pelo Edu.
Não precisa, aqui tem o Edu, mas tem a única visitante, qualquer um pode logar com... Você pode criar uma conta ou logar com o Google, Facebook.
Eu te mandar.
Não, eu sei.
Colocar no site.
Isso, agora você vai conseguir. Bom, a senha, você está falando na senha, é verdade.
Eu ponho lá para mandar o e-mail.
Teve um outra pessoa que teve problema com a senha também. Você consegue mandar por e-mail? Ele tem um pendrive? Não, beleza. Tem vírus?
Ele falou que tem um Ubuntu, então.
Tudo aqui.
Hello, everybody, and welcome to the first edition of FOSForums. Here with me, we have Rafael. I am Leonardo Garcia. I work for Leonardo. I am the chair of the Leonardo Data Center Group. We basically work with enabling ARM servers in open source ecosystems. Hello, everybody. Sound is working. With a huge delay, but yeah. That's what I'm basically doing. I work at Leonardo leading the Leonardo Data Center Group, enabling ARM servers on open source ecosystems. Rafael?
So, I'm Rafael. I'm a technical program manager at the Linux Foundation and RISC-V International. I compete with Leonardo because my goal is to make RISC-V the most successful platform or architecture across the globe. And yeah, so my job there essentially is to ensure that everyone, over 3,000 members, can contribute and define and develop the ISA, RISC-V ISAs, in a better shape as possible. And that they can contribute, and the partner or the members can also create products that everyone can use. We have a good amount of products or RISC-V based products out there. And yeah, my goal is to ensure that everyone can collaborate. I'm the only one in Brazil. And in Brazil, we're starting to get RISC-V growing. Next year, we're going to have a RISC-V day in March. But we have a lot of people already work RISC-V over here. So things are moving and happening in Brazil, but we are way behind the rest of the world. So my goal is to ensure we also put Brazil in the map.
All right, so even though we are competitors, we are here together for open source, free and open source, so that's okay. How this thinking started, right? So as everything that is very important usually starts at a bar thing, right? So we were meeting together in a happy hour with some friends from IBM. We both worked at IBM in the Linux Technology Center in the past. And Rafael started to talk to me that he was willing to produce a conference focused on open source hardware, right, in Brazil. And at the same time, the beginning of the year, I was thinking more or less the same, but of course my focus has been on software, right? So I said to him, you know what, we should get together and try to put these things going. And I shared with him, I think he wasn't aware of that, but back in 2013, myself and Tadeu Cascardo, we made an open source conference here in Brazil, in Campinas, at Unicamp as well, called Upstream, right? Which was had a good success at the time, more or less 100 attendees. So I said to Rafael, we should do that. Yeah, let's try to do that. Let's see if it's going to get some traction. And yeah, we set up some objectives for the conference, and it was good because we both had more or less the same ideas in mind, so it was not that difficult. So it would be focused, of course, in free and open source hardware and software, because we both have interest in both sides. Free to participate. We don't want to ask for a registration fee. English as the main language, and that was a little bit controversial with some people we talked to, right? Some people said, yeah, you're not going to be able to do that. We tried before, it's difficult, but we decided to stick with that, right?
So if you look at what's happening, especially on countries that compete with us, India and China especially, everything they do is mainly based in English. If you want to somehow expose Brazil and the people that are working here and the developers that are working here, we need to ensure they can propagate their work in a language that anyone can understand. So it's better to do something in English, even though it's not going to be perfect at the first time, but it's going to be something that we can show off. So if someone asks, hey, can you point me to a presentation about debugging? Okay, maybe we have someone here that did that presentation, you can point someone out in another account. So doing this in English is for us, I would say, is trying to open the door for people that does not know what we do in Brazil can also start to understand what we're doing over here.
Yeah, and when I was briefing some of my colleagues at Leonardo about this conference, the distinguished engineer there told me that, yeah, that's a great idea, because once I was invited to a conference in Ukraine, and of course some talks were in English, but the majority of the talks were in Ukraine. I don't know what is the name of the language, Ukraine or Russian or something like that. Anyway, an Slav language. And he said, it was bad because I was sitting there and I couldn't understand anything. I couldn't interact with the people. And I said, yeah, that's bad. I mean, we want this to be an international conference. Of course, that this year, the majority of the attendees are from Brazil. I will show that in a map later. But, in the end, we want to attract people from outside. And it's a good opportunity for people that is not very used to present in English as well to train their skills, right? I mean, everybody wants eventually to go to conferences outside Brazil. So it's a good opportunity here to have a safe audience, right, that, we can interact with. We wanted it to be located in a university. So we decided to do it at Unicamp because we have... lots of interactions here at Unicamp. Right?
Insiders.
Yeah. Well, I studied here. My undergraduation and my master's were here. Rafael has been here for quite a long time, managing the IBM lab inside Unicamp as well. So we have very good interactions with the people at the university here. During a weekend, that was another controversy, but we stick to the idea, right? Especially because we inspired, as I said before, I mean, I was inspired by Upstream that we did before, which was on a Friday and a Saturday and worked quite well. There is also FOSDEM, which is, at least for me, a big inspiration. I have been always a big fan of FOSDEM, and it's during a weekend. And I think this year they got like 8,000 people there. So it's really crazy, right? I mean,
they are cool, but they didn't allow us to use the FOSDEM name or something similar to that. So.
Yeah, that's not a problem. We got a better name, so that's okay. Okay, so of course that when we decided to start, it was like February when we had the first meeting. Things start to get more complicated, of course, right? I mean, we have to start to, do we want registrations? I mean, initially I thought that we wouldn't need registrations. Just come and get together. I think FOSDEM is like that. But in the end, I mean, it's quite difficult because we have to plan a space. Everybody that we were going to talk, they ask, how many people are you expecting? And I said, I don't know. I mean, it's the first time. How can I say? But anyway, so we decided to restrict to 100 attendees, more or less. It's the size of this auditorium, by the way. So we sold out. So it was great as well. Well, where we decided in the beginning, we wanted to be at the university. It was quite a challenge to get a room here at Unicamp. But Professor Rodolfo helped us with that. We tried some alternatives as well during the way. Hopefully next year with more time and more preparation, we can have a bigger space for a bigger audience as well. When we decided to be in August, just because it seems to be a good date. Very little conferences happening this time of the year because it's usually vacation time for the Northern Hemisphere. Volunteers, of course, we needed volunteers, right? So we have Luciano and Iago out there with the nice t-shirt. So they are helping us. Marketing was a big question as well, because we don't have budget, right? We were just trying to do a low-cost conference, and we didn't know how to announce this thing. So we decided to have no marketing. We will say, at LinkedIn, lots of people got my message at LinkedIn. I think that was the first message. We sent some emails to folks saying, this is happening. Could you please share this with your, company, within your university? And it was great. I mean, in the first 2 days, we had like 40 attendees registered already. So we were actually quite frightened by the number of attendees registering in the first initial days, because we said, we are going to sold out in a week. I mean, we thought, there was a need for this type of conference in Brazil, but the feedback was very positive in the beginning, right? So, I was glad that the rate of registrations declined with the time, right? But we were able to sold out. So, that's great, right? Without any big marketing and any kind of activity like that. And well, last but not least, the sponsors. I mean, of course, that initially we were not thinking about sponsorship, but it's hard because the moment you start to think about the conference, you start to spend money, right? So like, well, we need to register a domain name, right? Okay, that's $50, 50 reais, right? It's not very expensive, but you start, we tried 3 names, right? Before, concluding this one. So we have 3 domains registered. Then, of course, you need some tools. I mean, I need to write emails. I didn't want to write emails with my company email, right? I mean, so you start to spend money. I mean, it's impossible. So we decided, it was an afterthought, but we decided to launch a sponsorship. This year is especially not a good one because of the economic situation, but we were able to get 2 sponsors, so we are very happy about that as well.
Yeah. And they are covering the majority of the items here. So please, you eat all the food.
Yeah, please. And of course, especially for the speakers, we have some unexpected last-minute issues, right? So I'm not a web admin, or at least I'm not for the last, 15, 17 years. We are using an open source tool for the conference. It's called Pre-Talks. Very nice tool. Easy to configure. I mean, I spent like 8 hours to put together a virtual server running on an ARM processor. And I installed it. I mean, it's out of the box. I mean, you follow the installation instructions, it works. You have to dig with some of the configurations. But of course, I mean, I didn't test uploads of files before, just tiny photos for the avatars. And when I submitted my presentation, this presentation, everything worked. So it works on my machine, right? So it's working. Then I started to get some feedback saying, yeah, I'm getting this 413 error. What is going on? And I said, other people were able to submit. So I don't know what is happening. And of course, everybody everybody submitted the presentation in the past 48 hours. So I didn't have time to look at this until last night, because I got a request from a speaker to update their photo, and the photo was larger than 2 megabytes, and the person was not being able to upload the photo. And I said, oh man, I will have to do that, and I don't know exactly where to put the file inside the file system, right? So I decided to look at what error was going on. It was quite simple to fix that. So if you want to upload your presentation, now it is working, up to 32 megabytes. If you want more than that, talk to me. The limit was 2 megabytes, which is, for some reason, the default limit in Nginx. I don't know why. Anyway. Code of conduct. I mean, we don't have a specific code of conduct for this conference, right? We debated a little bit about that. We thought that this wasn't needed specifically because we think that Brazilian laws are already in place here, and they prohibit any kind of harassment, discrimination, and any kind of this thing. So we expect everybody to abide to Brazilian laws, and I hope that this is enough. But anyway, if anyone has any problem here during the conference, just come talk to me or Rafael, and we will try to fix that out, okay? Data privacy, that's something that we think a little bit in the beginning, but not very through.
Yep.
So in the beginning of the conference, we decided not to collect information about the attendees, right? Yep. And I think that's a good thing, right? I mean, I don't want to collect information about everybody. Of course, if I have a registration, I use the tool Eventbrite. You have to register to Eventbrite. I'm sorry about that. I wasn't going to put a tool for that. And I thought that Google Forms was not enough for this, because then all the work would be on us. So we collected your name and email, right? But of course, when you have sponsors, the sponsors want data, right? So they started to ask us, can we have a list of the attendees? And I said, okay, I cannot provide you that because Brazil has the LGPD law, right? Which is similar to the GDPR law in Europe, even more strict in some cases. So we are not going to provide your data to anyone, right? But if anyone, Well, actually, I mean, let me rephrase that. I mean, there is one sponsor, Husk, our sponsor. They want to send some messages to the attendees later after the conference, right? So if anyone has any problem with that, please come and talk to me, because I'll say them not to send emails to you, okay? But that's the only information that we are going to share.
Just the email, not the name.
Just the email, yeah, not the name. Okay, the email that you used to register to the conference. That's the only information we have anyway. So I want to thank you, our sponsors, right? Husk and Red Hat. We have also a number of partners. So Unicamp and Instituto de Computação, Institute of Computing. So that's where the conference is taking place, right? Professor Rodolfo helped us a lot with the interactions with the university and the institute to be able to use this space, which has a very, very nice infrastructure. You know, we're being able to stream to YouTube because they have everything set up. So that's great.
Risk 5,
yeah.
I believe he's going to be, we cannot say that word, but
the Institute for the Conservancy of Free Technologies, I'll talk a little bit about them later. That's a very nice non-profit organization that is helping us. And of course, Leonardo, I mean, the place where I work and that supported me through this endeavor. So I'd like to talk a little bit about Husky. So Husky is a fintech that was created back in 2016, right? It tries to make it easy to do international transfers for Brazilians, especially for tech professionals that are working remotely for companies abroad, such as me, for instance. So I use their service, by the way. You know, it's really a seamless, hassle-free payment solution. It's very easy to use. They were bought by Nomad back in 2022, right? And Nomad has a broader service. They are really an account for travelers, content creators, global workers, and investors. You can have your money all around the world. I mean, it's quite broad what they offer. Red Hat, I suppose everybody knows Red Hat. I mean, I've been using Red Hat since 2000, right? Yeah, no, 1999, yeah. So it's the leading provider of enterprise open source solutions. It has a broad portfolio of products and solutions based on open source software, right? I want to talk a little bit about the Instituto para a Conservação de Tecnologias Livres as well. The slides are in Portuguese because, you know, they are basically a Brazilian non-profit and their target is really to work with Brazilian projects. They try to be more or less like the Free Software Conservancy organization. I think Tadeu has a t-shirt from the Free Software Conservancy. So they try to do the same here. So it's very difficult for us, for instance. I mean, if you want to get a sponsor for a conference such as this, I mean, we don't have an enterprise, we don't have a company, right? So the sponsors usually they do not pay anything for a person. They want to pay for a nonprofit. So that's what the ICTL does. I mean, they are basically this legal institution that can receive funds and provide them to the projects and manage these funds, right? So, you know, as I said, I mean, for sponsorships, to pay for stuff as well. I mean, we have to pay for, I mean, that's not the case here. I mean, the place is for free for this conference, but if we had to pay, they could pay that for us. They could sign a contract, right? So it's very useful, right? And of course, to keep the money, right? Because, you know, it's very difficult to size exactly the amount of money. So sometimes you have some money left, so they can keep this money to the next year. They can manage all these things. So it's very helpful. So, I mean, these are the projects that they have. So they always organize them in Brazil. FOSForums, of course. DebConf 19, which was in Curitiba, they were the ones that organized that as well. They maintained FluSP, and they were also behind Linux Dev BR. I mean, they were the organization helping Linux Dev BR to manage their financial resources as well. So if anyone wants to learn more, these slides are available. And I would like also to thank the people that helped us through this endeavor, right? I mean, Rafael, he presented himself. Luciano and Iago are, you know, our volunteers. Thank you very much. Professor Rodolfo, I mentioned before. I mean, he has been helping us with the interaction with the university. Gabriel was a person that provided me a number of insights in the beginning about how to put together the infrastructure for the conference. He was responsible for the infrastructure for the Linux Dev BR conference. Guilherme was my beta tester, right? He was even able to register with a wrong email. That was good test. Gustavo and Bruno, they were behind Linux Dev BR and they helped with some of the funding challenges that we had. So thank you very much for them. Antonio Terceiro and Daniel, they are behind ICTL. They helped us a lot as well. Renato Golin, he was one of the organizers of FOSDEN and LVM. I didn't know him. He reached out to me through LinkedIn because of my first initial post about FOSForums, and he helped me with lots of insights about how to organize conferences. So thank you very much for him. And Cascardo, thank you very much. I mean, even though we were not involved in this conference specifically, I mentioned Upstream before, and I think you have always been a good inspiration for everybody that likes open source and free and open source in Brazil. So thank you all. As I said before, we didn't collect any information about you, right? But everybody asks about some demographics, statistics of the conference, right? So I stalked people and tried to put together some information that I can show to sponsors in the future, right? And I thought it was interesting to share with you as well. So this was based on your names, right? So I'm not making any judgment about your gender identity. I just read your names and thought, this might be a male or a female. That was it, right? Of course, as expected, we have much more males than females, right? But I was quite glad to have like 15-20% of females here. I think that's a good number to begin with. And other is just a statistic, right? Because I know that people might complain if I put just male and female. So I look through the internet and they say that more or less 9% of the population does not identify themselves as male or female. So we should have more or less the same amount of people that do not identify with male or female as attending the conference as well. Demographics. Well, as expected, the majority of the people is in Brazil, but there is one guy that, at least according to LinkedIn, is from Germany. I think he didn't register this morning. But anyway, it was quite a surprise to me, to be honest. So I'm willing to meet him and ask why he registered, if he's just around and decided to join us.
It's a free conference, I'm going to say. Let me hash with him.
I don't know. No, that's not the case. I mean, this is an important conference. He wants to be here.
Yeah.
The majority of the people is from the southeast and the south of Brazil, right? I think that's more or less expected as well, even though it's a free conference. It's the first edition. It's very difficult for people to justify traveling, right? And it's not cheap. And the majority of the people is from the Campinas region, right? I mean, the large majority from Campinas. São Paulo is this other bigger red dot there. And then we have all the cities around here, south of Minas Gerais. So as expected, right? Not a surprise. This data I collected from LinkedIn. So I just visit the profile of the ones that have profiles on LinkedIn. So it's very incomplete. Some people don't bother to put where they are from. So it's incomplete, but it's just to show some information about who is attending the conference, right? And last but not least, I mean, also collected from LinkedIn and from whoever I was able to find there. The majority of the folks attending here are students from Unicamp, so that's great. I mean, overall, I think 25% of the attendees that were registered are students. And then, Sene, the National Laboratory of Energy and Materials here in Campinas, they will provide 2 speeches this morning, and they have the largest audience, the largest number of attendees here. Red Hat, Canonical, USP, Igalia, Leonardo, Collabora. I mean, not a surprise, right? All companies that work with free and open source software so that they are, I mean, the majority of the attendees are from them. And then we have a huge collection of other companies and universities with 1 or 2 attendees, which is great as well, right? Because we don't want to be focused on just, very well-known companies. We want to have a broad range of attendees as well. Lunch break. Rafael was able to make a restaurant nearby here to open today and tomorrow, because usually they do not. I mean, it's a university. There is nobody here during the weekend. So it's a Unicamp. We are here at the Institute of Computing over there. So it's very close by, just down the street. They will be opened today and tomorrow. There is as well the university restaurant, which I suppose is open today and tomorrow as well. Do we have any students here that know if the restaurant just across the city is open? Just the big one?
No one.
No one?
This weekend.
No one? Really? When I studied at Unicamp, they opened during the weekend. I don't know. Well, students sit during the weekend, yeah. Anyway, so you have to find out where to have lunch. Unfortunately, we don't have any sponsors for the lunch this year, so we will have to go around. There are a number of other restaurants along the way for the ones that don't know Unicamp. So if you just exit through the physical education university here, so there is a number of restaurants in this avenue here as well. We will have a social event this evening. I know that probably very few people noticed that this was included in the agenda 2 days ago. It's just because, I mean, we thought it was a good opportunity during the day. Probably people will be much more focused on the talks and, trying to pay attention than really to interact with each other. In case you want to join us, unfortunately, we don't have a sponsorship for this as well, but we will be hanging out at the Lado B, which is not too far from here. It's a 6-minute ride by car, so it's not that far. The agenda for today, right? So we have this welcome coffee, then this welcome session. We have some time here until the first presentation starts, just for everybody to, get some more coffee, or no coffee, but, juice and bread cheese and, whatever food is out there. So you can get some more. And we will start at 10 a.m. with open hardware at Sirius Light Source from Danielle. And then just after that, open source software at the Sirius Light Source. Sirius is a great project. They will talk more about that. It's the largest scientific project in Brazil. We will have Carlos talking about LHC. Right? This is a hackerspace that we have in Campinas since 2011, right? So it's. I mean, there are a bunch of people that usually hang out there, so it's a nice place. Then we will have a talk from Renato about FreeBSD before lunch, right? And then after lunch, Guilherme will talk about debugging VM cores, or not necessarily VM cores, right? I mean crashes in the kernel. And then Leonardo Brás will talk about improving Linux for real-time workloads. We will have another coffee break without coffee in the afternoon. And then Helen will talk about sharing, scaling, collaborative testing, open CI ecosystem, a very interesting talk about how they are using Mesa 3D infrastructure to do OpenCI. Right? Did I get it right? Okay. And the last talk of the day is from Pedro, talking about the magic behind screencasting on Linux. Right? So we have a full agenda today. We expect to finish more or less around 6:20 p.m. And after that, we are going to the Lado B, if anyone is interested. Right? I would like to thank again our sponsors, and I think that's what I have. Rafael, do you want to say anything else?
So we have some time, so we have food, a lot of food out there, so ensure we consume everything else that's left behind.
Yeah, we have to take a picture of the audience.
Yeah, we need. And ensure you eat a lot, please. There's a lot of food there.
That's another important thing. I mean, when I talked about data privacy, we are going to take pictures during the event, right? So if you don't want your face and body to appear in our social media or our site, please let us know.
The same, I'm saying, same for the recording. We are recording everything that's happening here.
Yeah.
And later, we're going to publish that on YouTube or whatever. So if you're not comfortable doing that or not being present, I mean, if you do not want to show your face, we can manage to remove the face.
Yeah. Okay, thank you very much. I hope everybody has a nice day today and tomorrow. Thank you.
Beleza. Bom, vocês me ouvem bem daqui ou preciso de microfone? Bom dia a todos. Meu nome é Daniel Tavares, trabalho no Sene LNLS desde 2009. Eu estou aqui para falar sobre nossa experiência com o Open Hardware lá no LNLS. A gente começou a pensar nisso em 2011. Essa apresentação vai ser breve, mas eu acho que a gente vai ter bastante tempo para discutir, se tiver interesse em saber mais. Deixa eu passar aqui. Bom, aqui é só algumas fotos lá do Sirius. Então aqui é a vista aérea do prédio. E aqui são dois mundos mais ou menos separados. Ali em cima são elétrons e aqui fótons. Então, como alguns de vocês devem saber, a gente tem um acelerador de partículas lá, que é um síncrotron. E o síncrotron que a gente tem lá, ele acelera elétrons. São pacotes de elétrons viajando numa câmara de vácuo, num tubo, para produzir radiação síncrotron. Então imagina uma nuvem de elétrons viajando dentro desses tubos aí, passando por esses ímãs que conformam esse feixe ao longo da trajetória. E cada vez que esse feixe é defletido, ele gera radiação. E, no caso do Sirius, o acelerador é otimizado para gerar raio-x. E o raio-x é usado para sondar... desculpa, eu deveria falar em inglês, né? Agora que eu lembrei. Sorry. Switching to English. Sorry about that. So, these electrons, when they are deflected, they generate a radiation. Sirius is optimized for X-rays. And these X-rays, they are used to probe the matter. It can be biological tissues or semiconductors, any kind of materials. We have different beam lines to different kinds of materials. And so on the bottom you can see an X-ray detector. It's a pixel detector with each pixel has 55 micrometer. And so it's just to say that we have two words here. One is the electron beam and the other is the photon beams. So in this world of the electron beams, this is an schematic view of Sirius on the bottom. So those magnets that I just showed in the previous slide is showing these schematics here. So we just have to repeat this 20 times. So this is just one cell of Sirius. We have 20 of these. And we have some sensors to measure the beam position inside this vacuum chamber. These are these magenta points over here. And on the top, what I'm showing is the beam size. So the beam is not always with the same size. Imagine this cloud of electrons, and it's changing the size along the way as it travels along this tube. And what I want to show is that in the most stringent part, the smallest size of this beam is of the order of 2 micrometers. And we need to be stable down to 5% of this beam size. So it means that we need to measure variations of the position in the order of 100 nanometers or so. And this is where the open hardware journey starts. We needed to develop electronics to measure this position of these beams. And this is what we have today. So this is just one rack of 20 racks that we have in the machine. And we decided roughly in 2012 to do these electronics as open hardware projects. And we started studying what would be required for this. So this is basically radio frequency, digitizer, electronics. We need to receive some radio frequency signals, they'll convert this to the baseband and do a amplitude demodulation. And with this, we can measure the position inside that beam. Okay, so this is the boards that we developed as open hardware, and I think it's not worth giving much details of each of these projects. But what I wanted to show is that each of these electronics has a GitHub or Open Hardware repository link where you can access all the design files, and you're ready to manufacture by yourselves if you want. And I also wanted to put here not open designs on the right, those boards there, because we tried to follow standards as much as possible. So with this, we could combine open and not open designs. I think, I'm not sure, but maybe it's a bit different from software, but I think it's key to try to follow standards. Sometimes in hardware it's difficult to do everything open, so I think following these standards, it makes it much easier to combine these two different kind of designs. So in general, what these boards they do is process radio frequency signals. In Sirius, we have 500 megahertz signals, and provide a digitizer. So analog to digital converters to digitize the signals, FPGA boards to process all the signals, do the digital signal processing chains. And the most recent board here, this one, is a power amplifier that allows us to act on the beam to correct the trajectory in very high frequency. So we can measure in several points the position of the beam, calculate the control loss, and apply it to this power amplifier. All these we want to achieve. We're now running at 50 kilohertz update rate, but we want to achieve 100 kilohertz. So it's a quite fast control loop. And here I just wanted to highlight what I believe is the most successful designs in terms of adoption. I'll tell more later, but it's hard to have a massive adoption in the community. I will tell why later, but we had some other labs wanting to use these boards. So this picture from a colleague from Germany, in GSI laboratory, where they use the same board. This board is a FPGA design, FPGA board, generic board, where you can replace mezzanine I/O cards and achieve different roles for this board in a system. And on the bottom, I think, is an even more successful project it's not hardware, but it's a firmware that is used for housekeeping of this board on the top, this AMC FMC carrier. And it's a quite, let's say, small code. It's not a big project, but it's an infrastructure firmware used in many of these boards in this standard. It's called micro-TCA. So I think this nature of being a infrastructure code made it this adoption much higher than the other projects that I just showed. Here, just a few thoughts about our journey in open hardware. So first, I think we could imagine that it's quite hard to convince people from knowledge transfer. They usually have a different mindset of thinking about patents, protection, and even harder to convince companies that it's good to open designs. So we are still in this discussion with some progress, but it's something that we need to advance. It's quite hard to have this conversation. And as I just showed, we try to use standards, and I think it's essential. I would recommend this for sure for everyone that is doing hardware, not to customize too much, try to follow the standards. This will make it easier to get higher adoption. And just this may be too specific for us at Sirius and in our domain, is that the community is not too large. So if we look for people with similar interest in our community, we'll find just a few, I don't know, 3-5 people looking for using these boards. It's really hard to let's say, to achieve that magic of open source, of spontaneous contribution, someone that took this design, modified this, and we get back from them. It's a bit harder here because the community is very small. So this is a challenge. And I just didn't want to leave this talk without talking about these guys. This was where we took the inspiration from. Probably, I don't know if you know about this project, White Rabbit project. It's basically an Ethernet-based protocol to make use of the low level, the physical layer of these optical fiber transceivers to achieve sub-nanosecond timing. So you can distribute timestamps with a precision of nanoseconds or sub-nanosecond. And okay, this is just for curiosity, but what really interested us here is that throughout this project, they build all the foundation to open hardware. So they provide the open hardware license, that's CERN OHL, an open hardware repository. So they, together with the project they made, they built these foundations for open hardware. So we just followed the steps of these guys. So I invite you to try to know more about their experience too. And I think I don't have much time left, but similarly, for those who are in the open hardware domain, I think CERN open hardware license is a very well thought license, and it's worth a try if you are looking to open your design. So I just put some links. I think it's very interesting, the last link especially. It's very didactic explanations about the license. So there are good stuff there. It's almost my last slide. Is just to say that we didn't have this in mind when we started, but today we see as this open hardware initiative just as a piece of open science goal. So, and we have good alignment from LNLS upper management to try this goal. We're just in the beginning of this, but we can extend. And what matters here is just to try to achieve the sharing as a default. So you should have to, or at least I believe that you should justify if you're closing something, or if you're protecting something, not if you're just releasing to the public. If we want to be more romantic, it's just to think science as a big body of human knowledge spread, and we just contribute to this common good, let's say. But we are just in the beginning of this, but my point here is that LNLS has an alignment to do that and a support to achieve these goals. And this is just a summary. So I think it's important. What I wanted to show is that we do have electronics running at Sirius right now, 24/7, and with a large proportion of them are open source hardware. So it's an achievement. I again invite you to take a look at CERN Open Hardware License. I think it's the good one, the, let's say, most up-to-date license for hardware. And as I said, sharing as default is the goal for open science in general. And we are just a few, so we need critical mass. We need more people to think together about this. Otherwise, it will be quite hard to achieve these objectives. And just put some reading and video suggestions if you take these slides later. I strongly recommend you to take a look at this. Okay, we can discuss more in the breaks. Thank you very much.
So anyone has any questions? I mean, we have 2 more minutes. All right, thank you very much, Daniel.
So hi, good morning to all. My name is Eduardo. I'm here with Henrique.
Hi, I'm Henrique. I'm an undergraduate student here, and I'm currently an intern at Sene. So I'm working with Eduardo, so we'll show some things we work on our daily basis.
Okay, I cannot speak English as well as I speak Portuguese, but I will do my best, okay?
That's a problem.
So we are going to talk about open source software at Sirius Light Source. We have many teams in Sirius that work with software development. My team is one of them, where I work with Henrique. And let's go. First of all, I will talk a little bit about Sene. We are a non-profit organization which is mainly funded by the Ministry of Science, Technology and Innovation, but we also receive funds from other institutions, such as the Ministry of Education, FAPESP, FINEP, companies that come to develop some project with us to use our scientific infrastructure, and that's it. We have about 40 years of history. We started to build the first synchrotron light source in Brazil. It was named UVX, and it remained under operation until 2019. And today we have a new synchrotron light source, which is much more modern and how can I say? It allows us to make science in a really high level of quality, and that's it. Okay, Sene. For studies with, how can I say, it's focused on life sciences. It's going to be a lab for studying viruses and bacteria with the maximum level possible of biosecurity. So there, the scientists are going to work using clothes like an astronaut, because they are going to deal with an Ebola virus which is active, something like this. Okay? So let's go. So Sene has 4 lines of activity. We have many open facilities that receive researchers from Brazilian universities and also from abroad, especially Latin America. We also receive companies, industries from Brazil to perform some investigation in our infrastructure, product engineering. We also make in-house research, scientific research. We have many researchers in Sene, and also research and development from an engineering point of view. We develop scientific infrastructures. I will talk about it later. And we also develop projects with companies that have some partnership with us. Okay. We also have an innovation department who works with intellectual property, and they keep contact with Brazilian companies to to develop some projects with us. And we have many programs focused on education and training. We have internship programs for students, summer internship programs, scientific initiation projects, courses of short and medium duration focused on high school students, graduate students, high school teachers, graduate students that are enrolled in a graduate program from universities that are near to us. Sene doesn't have graduate programs, but we receive many students that come to perform to develop the thesis or for a master's program or a PhD program. So these students use our facilities to develop their job. We are located near Unicamp, just beside the data center of Banco Santander. So as Daniel told us earlier, Sirius is a synchrotron light source. It's a particle accelerator. It's not focused on the study of the origin of the matter, like LHC in CERN. It's just a big facility that acts like a big microscope to investigate the matter, okay? So what's the principle of a synchrotron light source? We keep an electron beam stored. This beam is used to produce synchrotron radiation, which is just electromagnetic radiation in a broad spectrum. And we filter this electromagnetic radiation to a specific range of the spectrum. Depending on the beamline, we want to use this light. And we put some sample in the front of this radiation. And we register the interaction of this radiation with the sample using a detector. A detector is like a camera, an X-ray camera, or a photodiode. It really registers the interaction between the sample and the radiation, okay? And the science we do with synchrotron radiation has application in many fields. So you can put a soil sample inside of the beam, or a protein crystal, a metal alloy, and so on, okay? And the Sirius beam lines are named after animals and plants that are commonly found in Brazil. I will talk a little bit about them later. Okay, we have 6 beam lines that are under operation. They are open for use, but Sirius is capable of 38 beam lines. We have other beam lines under construction, and Sirius is not ready. We cannot say it is ready. Okay, we are just in the beginning of the project, I say. We will have much more beam lines in the future and receive much more scientists and students in the next years. So this is an aerial view of Sirius. Here we have the main building. These are beam lines that are that come to the outside part of the building because they are really long. Okay, this is the longest beam line. I will show you in some details later. This is a view of the inside of the building. Here we have a concrete tunnel. It has about 1 meter of width, this wall of concrete. This is for radiation protection purposes, because when the beam is on, nobody can stay inside the tunnel because it's really hazardous. And this is the interior of the concrete tunnel. Here we have many magnets. The beam stays here in a small vacuum chamber. And these magnets are used to keep the beam stable and keep it in its orbit. Okay. Here we have the smallest beam line that is open right now in Sirius. It's called Imbuya. So this white wall is the wall of the concrete tunnel. It was only painted with white. Okay. And this beam line consists of a small optical table. This is a clean room. That's why I took the pictures from outside. If you want to go there, you have to wear a special clothes. Okay. And this is a really small beam line, but we also have bigger beam lines. So I will show you Carnaúba beam line, which is the biggest beam line we have there. The previous beam line is right here, okay? And the Carnaúba beam line, the biggest beam line we have in Sirius, starts here with this optical hutch, this white building. And it has about 145, 150 meters. So it starts here. Here we have the yellow floor, that is this one. And right over there we have the experimental hutch, when the science happens. So this is a picture of the Carnaúba experimental setup. It has many devices, many motors and motion stages. We have 5 detectors. And this picture is from a scientific paper about the Carnaúba beam line, and it shows what you can do with the beam line. The sample is placed right here. It is really small, okay? And we have a setup for cooling the sample with nitrogen, and many detectors to register the interaction between the sample and the beam. Okay, we have many subsystems that are needed to build a synchrotron light source. And we also need software to operate all these subsystems remotely from a control room. And that's my work, the work of my team, which is named Control Software Group. And we are going to talk about software operating all these subsystems remotely. We have other teams at Sirius that also work with software development. We have a team that is focused on data science, another that is focused on image processing. So it's like it's a team focused on applied mathematics, okay? Image processing. So my team and also my division, which has Daniel as the head, we also try to make every project as open source as possible, okay? But sometimes this is not possible. Sometimes we receive some source code from a supplier or from another lab, and the other person doesn't want to make this source code open source. Okay, and Sene has today about 1,000 people, and each people there has its own point of view about open source. So eventually, when we are going to talk with a lawyer of the company or with some guy of the intellectual property department, and this person never heard about open source, it's really hard to keep a conversation about open source, and it's really hard to convince this person to agree with you to make some project open source. Daniel told a little bit about this earlier. Okay? And today we contribute to many open source projects. Most of them are from the accelerators community, but we also contribute to projects that are not exclusive to the accelerator community. And in the future, we intend to be the leading figure of open source projects. But I really think it's hard to have a good idea to start a new open source software project that will become relevant. And it's really hard to put the sufficient workforce to make this project relevant. We are about 15 people in my team, and we are really, we are always occupied with many problems and many projects, and it's really hard to maintain everything working. So, putting too many workforce in a new project, sometimes it's not possible, okay? So, talking about software for Sirius operation, I wrote here 5 types of software we have. We have a device I/O layer, and Henrique will talk a little bit about it. Henrique works in this layer. We have user interfaces for experiment control. We have some scripts and task automation code. I will talk about it. Information systems, and also user interfaces for data processing. So, you can go on.
So, one of the biggest software framework we work on, and that's specific for accelerators, or it's mostly used in accelerators, is EPICS. It's called Experimental Physics and Industrial Control System. So the idea here is that we have a lot of equipment. Most of them talk a different language, different protocols, Modbus, or talks over internet, or many others way of communication. But we want a control room that can easily manipulate these devices remotely, as Eduardo told us before. So EPICS brings us a framework to make this setup, this distributed system, where several devices, here we don't list them, but all of the devices Daniel showed us, most of the ones we saw in images are controlled somehow in our control rooms and etc. So these devices, sometimes they speak only with one controller, the software, the manufacturer library, for instance. But we want everybody to talk with this device, and more than that, we want to talk the same language with all of them. So EPICS brings us a way to create IOCs, so input and output controllers, which will talk with the device and will expose process variables that we can change, for instance, voltage or the number of images a detector will acquire, and we'll provide it for several clients. For instance, user interfaces, the operators interfaces, alarm monitoring, so if some value goes outside our expected range, we want to be notified by it. So it's also important. And historian, it's a way to store the history of this process variable, so we can know what happened in the past, why some problem could have occurred, and many other benefits of having this logged. And also there are scripts for automation, so we want to change things at the same time so the experiment can happen. Sometimes this might be really fine-tuned, so we have also timing equipment that triggers signal to several equipments. So this all have to be controlled in a way the experiment can be successfully made. So this is the general architecture, and since we have several different equipments and some of them require high throughput, most of the IOC is written directly in C and C++, which will generate a optimized code that can deal with communicate with the device in the appropriate timing, let's say that way. And we also run these IOCs in servers, sometimes in our data center, sometimes locally, because of restrictions of the equipment or the protocol they use to communicate with the devices. And as I told you, there are several protocols that the devices use to communicate because there are specifics working and so on. So as I said, detectors is a case, and I'll talk a little bit more about that. Since one of the main parts is to capture what is the interaction from the beam line, from the beam with the material the researchers are studying, there are detectors that will capture this information, and there's a part of the EPICS framework that allow us to deal with area detectors, these kind of detectors, in a much more easily and consistent way. Here's a use case. So here's Paineira beamline. It's experimental station. This arc piece of pink.
The purple box.
The purple box, yeah.
Okay.
it is the detector. So this workstation is under construction. So there are several setup that is not assembled yet. But here's a use case of a diffraction case where the material the beam will hit the material and will detect, in this case in our arc, the image, the information of this. So here's an overview. I don't want to go to details. I don't think it's the right place, but I wanted to bring the idea here that we have a hardware layer where there is specific hardware, for instance, the detector we showed, that's developed to here with partnership with Pitec and national company. So we have the hardware layer, then the vendor API really knows how to communicate with the hardware, and then we bring the EPICS layers, which is porting this vendor API to EPICS, and then exploiting several processing software that's already written for EPICS in area detector. For instance, plugins for processing, for restricting the region of interest, and so on. And later, this will bring us to channel access, which is the protocol I told earlier that every device will communicate through EPICS. So here's a brief example of what I'm talking about. The detector will acquire an image. It will send it usually through Ethernet to a server that's ready for processing this image. We have an EPICS driver that knows how to control this equipment, and it will forward this image in a pipeline that the user, the beamline user in this case, will define. For instance, one may create a region of interest she want to analyze, and may transform it somehow, rotate it, flip it, or apply any other statistics in this way, or transformation. And in parallel, it might be saving the raw image, or we may save only the region of interest. So it's a framework that thinks of this variability between experience and use of the detector. And finally, this will be converted and provided in the network as through channel access to the operator interfaces and any other system we might want to consume, as I told her. And here's an example for our control. Let's say that way. In this case, is the accelerator control room. So everything about the daily basis of operating the accelerator itself is made in this room, and interfaces we put on this in the hands of the operators are mainly built with Python, with Piccoli, and which is actually ported to work with Epics. And also some systems were made in JavaScript with React, and so it's a web application instead of a local application. And
Okay, we have a missing slide, right? But no problem.
maybe the order was switched.
Yes.
Yeah, here I want to show you, it's a screenshot of one of the operators' interfaces. In this case, it's the diagnostics beam line. It's called the Carcara X, or Carcara X. And here is a picture that I took when the beam was on. So it's the real vision of the beam, let's say that way. Of course, it's not hitting directly the sensor of the camera. It is hitting a piezo and then going to the camera. But here we can see in the real proportion of the inside, let's say that way, the way the accelerator generated the clock.
Okay, so, well, Epics is a project that started in the USA in the 90s, and in the past years it received many funds from the USA government, and it's really popular in particle accelerators located in the US. So, well, we have many user interfaces for experiment control. As Henrique told, we use basically Python, Qt, and also PyDM, which means Python Display Manager. It's an Epics layer over PyQt with a visual editor for simple creating and running a GUI. And also we have some web interfaces based on React. React is our standard front-end framework for web interfaces. This is a picture of the control room of accelerators in Sirius, but each bin line has its own control room. Okay. When we are going to perform a scientific experiment in a Sirius bin line, we need to set up many parameters of various devices and also collect data from many devices. And here comes Blue Sky. Blue Sky is a project that was started in the US in a synchrotron facility. It's a layer over many Python popular libraries, scientific libraries such as NumPy, SciPy, and so on. And it also supports Epics for device I/O. And we intend to use this library. We are already using it for some bin lines, but we want to use it more in the future for experiment orchestration. It's automation of data collection at bin lines. This project has some facilities that are contributing to it, and that's it. Here's a diagram of the Blue Sky architecture. So you can have a central server that will receive the tasks that will be performed during the scans. We call a scan an automated procedure for performing a scientific experiment in a beamline. And you can use many popular libraries with Blue Sky for saving data, for streaming data to clients. There is a hardware abstraction layer that is compatible with Epics, but other similar systems can be used also. That's not our case. We use only Epics. And we intend to use Blue Sky in more scans in the future. We want to make it our default tool for scans. We also have some support information systems, such as a logbook for the operators when where they register all the events of the shifts. This picture shows a graph obtained from our historian tool, which is called Epics Archiver Appliance. It's a software that saves many samples of various machine parameters. It's not used for making science. It's used by our engineers and operators for diagnostics and to study machine problems. So this graph is from Thursday, when we had a problem with some devices at about 9 p.m. We also have tools for alarm monitoring and notification, but I'm not going to show them here, okay? And finally, we need user interfaces for data processing and visualization. So when we finish the scientific experiment, we have many data stored in our storage systems. And in the beginning of Sirius, we had many Python scripts and also Jupyter notebooks for data processing. But today, the scientists are not happy with this type of solution because we have many scientists that are not able to use a terminal or to interact with a notebook in the Jupyter platform. So we have a great demand for intuitive user interfaces for data processing and visualization. Well, we have an experience with Orange. Orange is a project led by a professor at the University of Ljubljana, Slovenia. It receives contributions from the particle accelerator community. It is based on Python and Qt and all the common scientific libraries that you use with Python. And we have a success case of Orange usage in the Imbuya beamline, the smallest beamline we have under operation today. I showed it earlier. And we are trying to use this type of user interface to make the data analysis and visualization processing easier for the scientists. So with Orange, you define visual workflows with these small balls. You place them here in this whiteboard and establish some connections between them to define the workflow for data processing and visualization. Orange is a great tool, but it only works if your data is stored in the machine where you run this interface. And this is not the case where we have a big amount of data produced by an X-ray detectors. You can run an experiment and obtain terabytes of data. So in these cases, the data is stored in our storage systems. We have about between 4 and 5 petabytes of storage capacity. in our facility. And to address these use cases where you want to process your data using an HPC cluster, we need different user interfaces. Orange is not suitable for these cases. So until now, we have talked about open source projects that were started outside Sirius, but this one we started this year there. We have here one of the developers, right there with the pink cap, Mateus. It's a web user interface called Deep Sirius, where you can define workflows for data processing in a visual manner and delegate the data processing to our HPC cluster. Okay. It is intended for use for some deep learning tasks. Okay, but in the future we can make it more general. And here we have a diagram of Deep Sirius architecture. We have a web UI and a backend that delegates to our HPC cluster the processing tasks. We use Slurm for managing the jobs in our HPC cluster. And we have here some guys that knows really well our HPC cluster also. So I put here 3 links with organizations we use today in GitHub. We are trying to organize all the repos in these organizations. In the past year, we started many organizations on GitHub, and this is not good. We need to have 1 or maybe 2 only, but it's an undergoing task. We have hundreds of repos, so it's not easy to organize them in a simple way in only one organization. So that's it. Thank you.
So do we have any questions to Eduardo or Henrique?
Hi. So I'm interested in the why open sourcing your code or your hardware is so hard. Not exactly hard for you, but from the presentation, it seems like you have quite some freedom to develop not only the code, the hardware, everything, technology, and so on. So it seems like it's yours. I mean, Sirius or the lab, but still you tell me that it's difficult to open source things. Can you explain me a bit more why it's hard? Do you understand my question?
Yes, there is some kind of brotherhood between accelerators worldwide, okay? But some labs doesn't want the open source mood, okay? I feel it from China, for instance. We don't have any source code received from a Chinese accelerator that is open source, okay? And sometimes we work with companies that doesn't want the open source model. So, for instance, in the past years we developed some X-ray detectors with a national company located here in Campinas. That purple boxes we showed in some pictures, and they don't agree with the open source model. And so these projects are not open source. Or are not fully open source. Only parts of the project are open source.
Do you know what are the disadvantages for the company specifically? Like, are they afraid of competition or so? Is that the case, or is there something else? I don't know. safety reasons? I don't know. Do you know anything about it?
Well, I guess Daniel can give a more assertive answer, but the company is not used with the open source model in this case.
Yeah, I think it's there is a, let's say, a mindset of protecting. Let's protect the design so that we can explore this with exclusivity. No other competitor can explore that. And I think it's understandable. And actually, it's not, just to be clear, it's not a problem of Brazil or Sirius, it's everywhere. So when we discuss with those guys from CERN, that I showed in my talk, they have the same issues, and they also are looking for ways to how to interact with companies. So one of the discussions, recently discussions we had with them is that maybe what is more successful is if when you build something inside the lab that is like a platform. So we could take our boards or this White Rabbit Ethernet-based equipment, and the lab is providing the platform, the big, let's say, the backbone of for the companies. They can manufacture, but the companies can build specializations of this technology. And these can be exclusive to the company. But the common platform is provided as open hardware or open source. So it's like like it happened with software. We are still finding the ways to how to make companies profit from these open technologies as well. And but okay, this is one thing. The other thing is sometimes it's difficult to open this discussion with people that is more focused on, let's say, patents, because it's just like patents are good. Somehow the index, how many patents you have, is a good thing. But in the end, what is this doing for innovation? If we as a national facility, a national lab, if we provide open technologies that Brazilian companies or even from abroad can explore that, I believe that this is better for innovation. Let's say, maybe it's not how the company will profit most, but for the innovation itself, it's better, because you cannot just wait for exploring the technology. This is my secret. I can know about what is in the design, and if you do it open, so it will move much faster, because you cannot stop. You must innovate every time. You cannot just sit on top of this innovation and wait until you get rich in your company. So this is how I think we should try to show to the lab that this is fostering innovation. Maybe this should be our point of view: innovation, not what the companies can make money out of this. And I think for the whole ecosystem, this will be healthier than thinking about only a few companies to get, let's say, the prize of this technology. I don't know. Maybe I don't know if it answers your question.
It does. It does actually. Thank you very much.
Hi, thanks for the presentation. Before, I think like 2 slides ago, you mentioned the HPC cluster and how you set jobs. However, on this talk, there were times that you use overview tools as Python, PT, and all this stuff. So I'm trying to get how do you guarantee the throughput of getting this low, I guess it's a lot of data underneath the hood. So how do you guarantee the throughput? And also, another question, if I may, you did mention before that you also work on, you use a lot of Linux servers. So on these other appliances that you're creating, the hardware and all this stuff, do you use like any real-time Linux on top of the kernel?
Okay.
Sorry.
No problem. But we can share the reply, I guess.
Yes, for low throughputs, there is nothing special, okay?
Okay.
But for high throughputs or X-ray detectors, we have a storage system that uses the lustre file system, okay? So we use this for high throughput case.
Yeah, most of the data, let's say the book data, is coming from the experiments. So, like I said, there is the electrons and photons. So, in the photon side, because we have these X-rays hitting a sample and then hitting a detector, and we have to collect the data from the detector, and that is where the massive data comes from. And these guys here, Leonardo and Mateus, they were responsible to assembling our high-throughput data center. It's called Tepui, and this is where we have these high-performance storages, HPC. This is quite different work from the control of the machine, of the accelerators, where the throughput is not so high. We have different optimizations, let's say. And yeah, so just for complementing what Eduardo was saying. And okay, so for those electronics that I showed, each of those crates has a CPU, and this CPU is the server who is providing these variables to the control room, let's say.
Okay.
And this is still running on CentOS, right?
Yes, CentOS 7.
We want to change that, but for now it's CentOS. But there's no need for real time, because all the real time stuff, and we do need, is done inside the FPGA, so in hardware. But in some labs they use real time because the control loop is running on the CPU, but it's not our case.
Got it.
We have tried real-time Linux in the past, but today all the real-time part of our systems are at the FPGA level, at the hardware level, okay?
Yes.
And maybe we have real-time Linux inside some commercial equipment, a motion controller in the state of art. That's possible. But we buy these equipments and use it.
Yeah.
We don't, no matter what is inside
You
it.
said that some of them you don't even have access to the.
Yes, we develop hardware, but we also buy commercial off-the-shelf hardware. Okay.
Okay, thank you very much.
First of all, this is a presentation in Portuguese. I'm sorry. I'm here to talk about a very regional thing. So it's supposed to be in Portuguese, but they just mentioned right now that it's in English. Anyway, so I will switch to Portuguese. And if you have any questions in English, I'll be glad to answer. Ok? Eu sou o Carlos, tá? Eu vim aqui para falar para vocês conhecerem o Laboratório Hacker de Campinas, o LHC. Muita gente aqui já conhece, mas quem não conhece, essa é a oportunidade. Eu tô com 22 anos nessa vida, faço software desde o início dos anos 2000. E eu frequento o LHC desde 2016. No início eu estava muito interessado em Arduino, eletrônica, eu já tinha uma base de Python, tem uma comunidade de Python muito grande aqui em Campinas. E frequento desde então, né? Então, assim, mais da metade do meu tempo eu estou dedicado a um grupo de mentoria que investiga tudo relacionado com tecnologias de FPV, drones de racing, por aí vai. Eu monto meus próprios drones, desenho meus próprios drones hoje em dia, tá? Mas, assim, o que me levou para o LHC foi que lá em 2016 eu nem sabia soldar, para vocês terem uma ideia. Então foi num hackerspace que eu comecei a me desenvolver na área de eletrônica e embarcados. E enfim. E assim, o que é o LHC? Eu gosto muito da ideia da cultura maker, né? Um espaço cultural como a maioria dos espaços culturais, mas esse é diferente. É um espaço de cultura maker. Você vai para lá para mexer em qualquer coisa que envolva tecnologia de uma maneira geral. E outras coisas também. A gente tem uma cozinha bem equipada e o pessoal faz cerveja lá. Com rótulo próprio do LHC e está sempre à disposição lá para comprar. Assim, não é que esteja sempre à disposição, às vezes acaba na primeira semana. Tá? Mas enfim. A gente tem de tudo lá. A gente tem pessoas envolvidas com mecânica, com computação, com eletrônica, pessoas que vão lá só para jogar RPG, pessoal que faz cerveja, o meu grupo que mexe com FPV e por aí vai. Tá, mas como que funciona o LHC? Ele é uma casa física com associados, com pessoas que se associam através de a gente tem um esquema de associação e que você tem direito a uma chave e você pode entrar na casa na hora que você quiser. Literalmente, se você quiser ir de madrugada para lá no domingo à noite, pode ir, cara. Você tem a chave. E o que você pode fazer lá? Cara, qualquer coisa desde que você seja respeitoso. E quando eu falo qualquer coisa, eu falo qualquer coisa mesmo. Eu tenho um colega que fez um lança-chamas. Né? Pra vocês terem uma ideia, ele construiu um lança-chamas, uma bazuca. Enfim, para vocês terem uma ideia do que é possível fazer. Tá, a gente se organiza através de uma associação. Deixa eu... voltando aqui. A gente se organiza através de uma associação, que foi formada tem pouco tempo. Essa associação ela tem uma assembleia mensal que ocorre online e uma assembleia ordinária que ocorre a cada 2 anos para a eleição de diretoria. Essa associação é uma pessoa jurídica, ou seja, é uma PJ, ela não tem lucro, todo o dinheiro é revertido para a própria mantenabilidade do espaço. A gente tem mais ou menos 25 associados. Os valores eles variam entre R$ 85 e R$ 120 por mês. A gente tem um esquema de pagamento via PayPal, você paga um link recorrente de pagamento, aceitou, tá valendo. Tá? Mas a gente tem um processo de associação. Eu vou entrar nesses detalhes. Então, como eu disse, eu vejo mais um hackerspace como um espaço cultural, de cultura maker. Mas essa é uma definição que varia, tem várias definições. O principal delas é aonde esse hackerspace ele é reconhecido como um hackerspace. No caso do LHC, a Associação Internacional da qual nós fazemos parte desde o início é o hackerspace.org. Se você entrar nesse site do hackerspace.org, você vai ver hackerspaces em todo o Brasil já, não só nós. Tem o Garoa, quem conhece o Garoa Clube de São Paulo também. Então, a gente está envolvido nessa questão de trazer as pessoas para dentro do hackerspace, para que as pessoas possam trocar ideia, para que você possa encontrar-se. Tem muita gente que tá, estudante principalmente, está no início da carreira, não sabe muito bem o que fazer. Vai lá e, poxa, se relaciona com outras pessoas, participa dos eventos e acaba se achando. Muita gente é assim. Mas é basicamente um evento, um local para você colaborar entre grupos e colaborar internacionalmente. Tá, e aí como é que surgiu isso? Em 2011 começou as primeiras discussões. Algumas pessoas conhecem o Leandro, que foi o principal fundador, né? E ali, por meados de outubro de 2011, eles decidiram fazer um hackerspace em Campinas. A primeira casa que de fato foi alugada para isso foi a famosa Casa da Vila Industrial, que nós ficamos lá até 2019, 2020. De lá, já na nova configuração, em 2019 nós fizemos uma assembleia. A gente tem um estatuto, ele foi todo escrito no GitHub, a gente aceitou patch de várias pessoas. Esse estatuto define o regimento geral de como funciona. Além disso, a gente tem também o regimento interno, esse é mais flexível, mas o estatuto é o que garante como é a configuração da casa. Nesse estatuto, 4 pessoas são eleitas para um termo de 2 anos e podem ser reeleitas mais uma vez. A primeira diretoria, algumas pessoas conhecem o Douglas, aqui, o Helen também, muito conhecido na comunidade Python, eu e o Alex, o X. O Douglas é o nosso presidente, é ele que é o rosto internacional do LHC, inclusive estava na Europa agora falando, nos representando no CCC. O René é o nosso tesoureiro, todas as finanças é ele que sabe. Todas as despesas da casa é ele que administra. Para vocês terem uma ideia de como era antes, a casa era alugada no nome de alguém, fulano pedia uma internet para casa, aí o ciclano chegava e pagava a conta de luz. Era assim que era organizado. Hoje não. Com uma assembleia, com uma entidade tomando conta da casa, a gente está tudo no nome dessa entidade e a gente só elege os diretores que cuidam do básico. É uma estrutura muito flat. Existem os diretores porque é uma questão legal. Tem que ter alguém dirigindo o espaço. E é isso. E aí, como eu falei para vocês, mais ou menos 25 associados pagam mensalmente. A gente tem alguns números aqui, vocês conseguem ver, mas varia entre 75, 85 até 217 reais. Ele paga em dólar, por isso que... Enfim, e esses 25 associados, mas tudo que a gente arrecada em eventos, mas tudo que as pessoas consomem da geladeira, sim, existe uma geladeira, ela está abarrotada de refrigerante, cerveja, água, enfim. As pessoas que frequentam a casa tiram o que precisam da geladeira e pagam. É completamente na confiança. Mas essas são basicamente as formas como a gente sobrevive. Existem outras? Existem. A gente vive muito de doação. Para vocês terem uma ideia, a gente recebeu uma doação recente, estava falando para o Leonardo, de ferro de solda para poder organizar um evento grande de eletrônica para crianças. E, enfim, vocês têm uma ideia de como funciona. E aí a gente disponibiliza um laboratório completo de eletrônica, com plaquinhas à vontade, tudo que você precisar está lá. É só abrir um armário e procurar o que você quer. Arduino, algumas coisas de SP32 e por aí vai. A gente tem a marcenaria, a cozinha, um salão enorme na parte de cima da casa. Cabe umas 60 pessoas, nós fizemos um evento recente com isso. E agora, estamos funcionando como cowork. Então, se você é um associado, chega lá para trabalhar, vai ter gente trabalhando provavelmente, e é uma oportunidade, mesmo que você não trabalhe na mesma firma do cara, é uma oportunidade de você conhecer pessoas. E aí, falando o que acontece no LHC. Sim, o Stalma, quando vem no Brasil, ele vai no LHC. A gente tem todo tipo de evento de comunidade. Grupai. Hoje mesmo está acontecendo um evento de pegar bandeira, cat flag, né? De segurança. Agora, nesse momento, está rolando. E a nossa mais importante conferência, que agora ocorre de forma anual, desde a pandemia ter acabado, que é a TosConf, a única conferência tosca do mundo. É tosca, velho, mas porque a gente fala assim que ela não é pela organização, é que a gente aceita qualquer trabalho. Ano passado tinha um cara ensinando a fazer refrigerante gasificado usando uma folha que eu nunca tinha visto, uma coisa completamente... Nossa, que da hora, sabe? Enfim, a gente já teve um cara ensinando a fazer espadas, ele levou um forninho, ele derreteu metal, ele ensinou a bater e tal. Foi muito bacana. Enfim, é muito bacana o lugar. Tá? Não é só tecnologia, é muito mais coisa. E aí vem a questão, como é que vocês se associam? Né? Então, a gente tem essa questão de você procurar um associado que vai te introduzir no espaço. Ele vai funcionar como mentor. Você tem um interesse, você procura a pessoa, você quer aprender FPV, você quer voar de drones, beleza, você me procura, eu vou te trazer para dentro do LHC e vou te colocar no meu grupo e junto com as outras pessoas que também mexem com isso, a gente vai te colocar no hobby, vamos dizer assim. Normalmente o processo é, você traz a pessoa, no mês seguinte ela se associa. Então ela de fato entra e recebe a chave no mês seguinte. Por que isso é importante? A gente precisa conhecer as pessoas. Você não pode simplesmente querer se associar. Quem é você? O que você faz e tal. Ajuda para que a gente não tenha qualquer pessoa entrando, enfim. Então essa pessoa que vai te encaminhar pelo primeiro mês, ele funciona como um mentor. Na reunião, você vai entrar na reunião também, a reunião mensal, ele vai dizer, estou trazendo aqui o fulano, ele está entrando, ele vai participar... vai participar do grupo de DevOps. Tem um grupo de DevOps enorme que se reúne praticamente toda semana. O Grupai de Python é gigantesco. Eles fazem umas festas com pizza lá, que é da hora pra caramba. Enfim, é isso. E as regras para se associar estão todas escritas no nosso regimento interno. Tá? O nosso GitHub LHC, para quem quiser ver. Por que se associar? Como eu falei, ter a chave do espaço e você poder entrar 24 horas, 7 dias por semana. O associado ele também tem direito a guardar uma caixa com algumas coisas dele lá. Tá? Então você pode botar o seu nome na caixa, as pessoas respeitam. E aí você é associado, você participa tanto da gestão financeira, então, as decisões de onde a gente vai investir o dinheiro que a gente arrecada. E você está fazendo parte do maior hackspace do Brasil. É arriscado dizer isso, né? Mas veja bem, o número de associados, o LHC é o maior do Brasil hoje. E a gente tende a crescer. A ideia é, nós estamos numa casa hoje e provavelmente, se a gente dobrar o número de associados, vamos precisar de um outro espaço. Enfim. E é isso, gente. Aqui é a nossa casa, tá? A gente fica na rua Araribóia, na Ponte Preta. Tá? Qualquer doação que você queira fazer, qualquer Pix, manda pro Batman. Tá? E o nosso canal do Telegram, eu convido todo mundo a participar, a dar uma olhada, a ir lá um dia, a comparecer, fala no nosso canal do Telegram e pergunta quando é que vai ter um evento. A gente tem um link só de eventos.lhc.net.br. Lá também dá para ver o que está rolando. todos os dias. Né? E é isso. Muito obrigado. Perguntinha, por favor.
Eu só queria clarificar, né, um mito, porque na época que eu participava, eu fui uma associada já há uns anos, e na casa antiga, eu não conheço, né?
Na Vila Industrial.
Sim, muito bacana o espaço. E eu queria só, porque na época, né, não precisava necessariamente se associar para participar, né? Bastava...
Você pode chegar em qualquer dia, em qualquer evento aberto. Como eu disse, hoje mesmo está tendo um evento e a porta está aberta, foi avisado nos meios de comunicação do LHC de que estaria de porta aberta para quem quiser entrar. O que costuma acontecer é que você pode chegar lá e não encontrar ninguém. E aí você não tem chave, você não entra. A gente convida as pessoas a se associarem porque não é só você chegar lá no dia do evento. Você vai querer ir lá para trabalhar. Muita gente aqui faz home office. Aquele dia que você quer trabalhar num lugar diferente, você pode ir para o LHC. A gente tem um link de internet bom lá. Mesas à vontade, enfim. Talvez isso é o que tenha mudado um pouco de lá para cá. É que na pandemia, por exemplo, quase não ia ninguém. Praticamente ficamos fechados. Mas deu para se manter, ainda assim. Perdemos alguns associados e tal, mas levantamos a cabeça e agora o que está diferente daquela época é que você precisa de uma pessoa para te mentorar na entrada do LHC. Entendeu? A única diferença dessa época para cá. Antigamente você chegava lá e dizia, quero me associar, então paga aqui, beleza, toma, tua chave. Agora não, agora tem um processinho, mas é um processinho só de praxe, para que todo mundo saiba quem você é, e também para você se acostumar com a rotina que a gente tem de reuniões mensais, assembleia, quem é quem. É muito importante saber quem é o Douglas, por exemplo. Você está lá no LHC e não sabe quem é o Douglas? É complexo. Enfim, é basicamente isso. Não sei se eu respondi. Legal.
Obrigado, Carlos.
Hello, everyone. Thank you to be here. I'm glad to be here today to talk a little bit about the operating system I like a lot, which is FreeBSD. My name is Renato. I am a software engineer at Netgate. And if you don't know, Netgate is the company behind the pfSense project, which is a really successful open source firewall project. And it's based on FreeBSD. And here's the agenda for today. I'm gonna talk a little bit about the FreeBSD history and what it is and why people choose to use it. I'll mention some companies and some projects that use FreeBSD as a base of their products, and why you should try to use it or contribute to use it. And it's basically Leonardo invited me to talk a bit about FreeBSD just to show like there is something different and maybe you never heard about it. So it's always good to know. The next slides are like more verbose than they should be, but you can read it if you want after the talk. But I'll go really quickly about it because it's hard to talk about FreeBSD without talking about the Unix history, because it's nice to see where it came from. So Unix was started by Dennis Ritchie and Ken Thompson in 1969 after a failure project called Multics. They have hardware available and said, let's do an operating system for that hardware. And they wrote Unix for the PDP machines, and it was like a really nice project. And it was written in assembler for that specific hardware. And after some years, they needed to port that code to another platform, and it's hard to port assembler code to different platforms. And they had a brilliant idea to write a more high-level language, and they came up with the C language. So the C language we still use today was created 40 years ago by the same guys who created the Unix operating systems. And Unix had proprietary code, but you could buy like a source license. So you could have access to the license, and if you pay for that. And someone at the Berkeley University in California decided to buy the source license, and students got access to that. And it was very, very nice for the students to have access to such code and to have access to a shiny new operating system. And they started at the computer science of Berkeley. They started to modify it and modify that code and make experiments, writing tools for that. And they called that Berkeley Unix or BSD, and they distributed that, few copies of that. But they are touching proprietary code, so they need to respect the license and everything. And then they decided to change that format. Instead of modifying the original Unix code, they started to add their tools on an add-on called Berkeley Software Distribution, BSD. And they distributed like that big roll tapes with the BSD software. So you could install that on top of the Unix system you have running on your company or on your university or whatever. And on the second version of BSD, the most important developer from that time was Bill Joy. And Bill Joy wrote the EX editor, and after that he wrote the visual editor for EX called VI, which is the VI editor that is based for Vim, and VI is still available, and there are different flavors of that available till today. And he also wrote the C shell, which he was not probably so proud about it. But back in the, later that in the 80s, Well, Bill Joy wrote some papers about Unix and about BSD, and DARPA was looking for an operating system for their military stuff, and they was really interested on that papers, so they decided to put some money on it, and they started funding the BSD development inside Berkeley University, and it was really important for the project because when you have more money, it's easy to accomplish stuff you want. And Bill Joy left. Bill Joy left to co-found Sun Microsystems, and the BSD kept going inside Berkeley. The 4.2 release was like one of the most important releases for the project. And instead of distributing like 75 copies, they distributed over 1,000 copies of this version. And it was the first time the mascot, the Beastie, was created, which is the mascot of the FreeBSD project until today. And it was printed in the manual pages distributed at Usenix. After that, the developers started moving out from VAX platforms and going to modern platforms like Powered 632. And the BSD team wrote support for that platform called Tahoe. And it was important because they needed to separate the part of the code which was machine dependent and independent. And it was good for the project in the future to start supporting different platforms. So now we come to the most interesting part for the FreeBSD itself, which is the start of the 90s when Linux was being showing up. So Linus started Linux in 1991, and at that time they have access to the shiny new Intel 386 platform. And then they decided to separate the proprietary code from AT&T and create a completely new operating system. They call it that Net2. And they distributed that. And people, you say that BSD guys are good to write code, but they are not so good to coming up with names. So they created two different products, one free called 386 BSD, and one proprietary called BSD 386. So, yeah. And they created the Berkeley Software Design BSDI company, which was the one that held the license for the proprietary code, the BSD 386. And this 386 BSD had a short life, and people decided to split that into two different projects. And here is when things became complicated because, there would be like a battle for operating system at that point. So Linux and BSDs are the options that would be possible to use. And so the BSD contained some proprietary code inside it yet. And there was a lawsuit, and that ends only in 1994. So AT&T said, hey, you have my code, and it's wrong. And, lawsuits. And after that, from 18,000 files, they needed to remove 3 files only. And they needed to modify 7 files, adding USL copyrights, and the legal battle settled. And at that point, Linux was adopted first, so it had more chances to grow up as it happened. And they created FreeBSD in 1993. So 386 BSD was split into FreeBSD and NetBSD, 2 different projects created by 2 different teams, maintained by 2 different teams. They came from the same place, but they are completely different. And after that, NetBSD was forked 3 years later, creating OpenBSD. And FreeBSD was forked later too, during the version 4, creating Dragonfly BSD. So those are the major flavors of BSD available today: Net, Free, Open, and Dragonfly. So yes, we are 30 years old this year. We are celebrating. It's a long history for an open source project, and there are lots of open source projects coming and going all the time, so it's hard to become alive. So basically, this is how I see the picture. It's a AT&T Unix on top, after that 386 BSD, and then FreeBSD and NetBSD. This is how everything started. I put this picture here. I know you can't read that, but it's most like to see what you can see in green. The green boxes are open source code, so open source projects. Here we have the 386 BSD, FreeBSD here. Here we have another version of BSD that was released after the 4.3. This is BSD 4.4, and FreeBSD also consumed code from that. Here we have NetBSD, Dragonfly is here, OpenBSD is here. Linux is separate, it's a completely separate project. And what you see in yellow is shared code that is a mix of proprietary and free code. And those ones are the proprietary Unixes, ANX, HP UX, Solaris is here, UnixWare, and STO, STO, and SunOS. When Bill Joy left BSD and co-founded Sun Microsystems, they started SunOS. And here's a closer picture to the BSD part and Linux and Linux on that side. So what is FreeBSD? FreeBSD is not a Linux distribution, and I'm saying that because a lot of people say that, oh, this is like a Linux distribution. No, it's not. It's a completely different code base maintained by other people and with different licensing, and you see that they are different. So what it is, it's really old project, it's large, and it's successful open source project. Different from we talk about Linux, we are usually talking about a Linux distribution. There are lots of them, and Linux is the kernel, and you have userland utilities from GNU, Free Software Foundation, and other places, and you have the distributions like Ubuntu and CentOS, Fedora, Red Hat. They get all this code and get everything together, package that, and distribute that, and take care of it, of patches, security fixes, and everything. So FreeBSD is a complete operating system. So if you look into the FreeBSD source repository, there's not only a kernel, it's a complete operating system, which is maintained together. And we also offer a package repository with more than 30,000 packages available. So you can install on your FreeBSD station things like Bash, which is the shell, the default shell for Linux, for most Linux distributions, I think. But on FreeBSD, it's not part of the base operating system, but you can install that. You can install the most well-known desktop environments like KDE, GNOME, Mate, Cinnamon, XFace, i3, whatever. And you have lots of things available to install on your FreeBSD station, depending on what you want to do with that. So here we have some data. We have like over 400 active developers, committers, to the project and thousands of contributors. We support the most important architectures. So we have Intel and AMD x86 32, not for so long, because the FreeBSD 14, which is being released now, the release process started this week, is the last version that's going to support 32-bit platform. So x86 and ARM 32-bits are gone on FreeBSD 15. We support ARM, RISC-V. Sene is here. Yeah. We support RISC-V. Actually, FreeBSD was founded by DARPA to write RISC-V support, and it was the first operating system to have a bootable RISC-V in 3 back in 2016, I think. I don't remember. PowerPC. There are some Brazilian guys that use it to work on PowerPC stuff for FreeBSD. People from you?
Eduardo. This guy over there.
Yes.
Alfredo.
Alfredo?
Yes.
Oh, nice to meet you. I see your names on the mailing list, but yeah, nice to meet you. And we also, FreeBSD is also available on AWS, Azure, and Google Cloud Platform. And recently, FreeBSD was ported to boot on Firecracker from Amazon. And it's impressive. Colin Percival did a really impressive work on that. It's booting in 20 milliseconds. It's really, really nice to see. There's some paper floating around with his work. And we have lots of deployed systems for many different purposes. And we can see some companies that use FreeBSD on their products. As I mentioned, Netgate, the company I work for, owns the pfSense, and pfSense is a really nice firewall, open source firewall, which runs on FreeBSD. Netflix created an appliance called OpenConnect, and it is a hardware, single unit hardware, that they distribute to ISPs all around the world to cache their content. And they run FreeBSD current, which is the development version of the operating system. They don't run the release version. They run the development version on their appliances, the OpenConnect appliance. And so probably if you when you are watching a Netflix movie, you are getting the content from your local ISP cache running FreeBSD on it. You are not going to the CDN to get their content. You do it once, but then the content is cached and you get it directly from the ISP, which is a really nice solution. Well, Sony on PlayStation 4 and 5. PlayStation 4 and 5 run FreeBSD as the base operating system. And it's a very good marketing for us. So, Apple, so macOS, yeah. After macOS 9, when Steve Jobs went back, they brought the next step code with him and mixed a bit of that Mac kernel with BSD content from FreeBSD and NetBSD and created the macOS 10, which is the macOS still being used today. And there are other companies using that. So the DNS root servers, I know at least ISC runs FreeBSD, so when you are resolving names, you're probably reaching some BSD stuff on the internet every day. So why you should try that? FreeBSD has an excellent documentation. Since the project is singular and maintained, it's the complete stuff and maintained by one team. You have the FreeBSD handbook, which is really big and covered the most important parts of the system. And we have a documentation team that actually upgrades that all the time. So when new features come up, they go to the handbook and upgrades that. And so if something is happening here on the source base, handbook will reflect that as soon as possible, and it usually very fast to happen. We have a friendly and approachable community. It's people are always available to help, to answer questions, and I'm part of the groups of FreeBSD in Brazil and the international mailing lists, forums, and there are always people trying to help. We are also on IRC yet. I don't know if all of you knows IRC, but we are still there. Yeah, we're moving to Matrix. It's modern, but it's not ready yet. But we are moving to Matrix, and we are moving to that because there are breaches for IRC. yeah. There is that cartoon about the IRC.
Yes.
There's a breach for that. We have modern compilers. I was having a conversation on the break about LLVM, and when FreeBSD moved to the default compiler on FreeBSD is Clang, and we moved to that years ago. But we have also GCC available on ports on package repository. You can install that, but the default one is LLVM Clang. We have the license. So yeah, I'm not going to the flaming war between GPL and BSD license, please. But for companies, it's interesting to have a more permissive license, and FreeBSD is distributed under the 2-clause BSD license, which is a 2 paragraphs license, really simple, and it's permissive, and that's why Sony did the PlayStation 4 and 5, and it's closed source. You can get the FreeBSD source, modify it, and you don't need to show people what you did. It's like that. That's the main difference between BSD and GPL. You don't need to give the code back. So for companies looking for a solid operating system to use as a base for their products, and for companies that don't want to go to the open source world, like to close that source code, they have on FreeBSD a good option to start. Here is how the project is kept on Git repositories. We have our own Git server, but we replicate the content to GitHub. So the source of truth is our own Git server maintained by our infrastructure team. And we public that code on GitHub too. And it's a policy of the project to hold in-house all the environment. So we have 3 main repositories. We have the source repository. This is where the kernel and userland tools are. So if you look at the source repository, you're gonna see a directory called sys, and it's where the code of the kernel is. You have contrib for code that come from external projects that are maintained on Git subtrees. And then you have all the build structure to consume that and create the final operating system for you. We have libc, we have compilers, and then we have the tools you use on the daily basis, like ls and sad and grep and everything. All the code stuff is on the same repository. We have the ports repository, which is the one responsible to create the binary packages repository. So historically, ports is like a bunch of make files. This is the area I work on the project, by the way. Ports is a bunch of make files split in different categories to help you to get one program installed on your system. So if you go like to the shells/bash and type make, it's going to download the bash source code, the tarball from bash server, and it's going to uncompress that, apply needed patches when patches are needed, because not all software are compatible with the system. And it's going to build and install it for you on your system. And it's going to keep a record of that installed package. It's the same as you install a binary package, typing package install bash. But you have the option to build it on your system and keep the same database tracking what you have installed. So it's good because it's highly customizable, because the ports tree offer options for you that are not options you can configure later. So imagine you have a software that during the build time you need to choose if you are going to use MySQL or Postgre, and you need to choose that. So you can do it. The port will show you a dialog. You can mark the options you want to build or not, and it's going to build a custom package for you. You have tools to do a massive build of these custom packages and create your own repository if you need. Let's say you need to keep 100 FreeBSD servers that consumes special packages with custom options. So you have a tool that you list the options, and you say build all these packages and all their dependencies and create a repository for me. And then you configure that repository on top of the regular one. And you say this is high priority, so consume packages from this first. And then you can distribute these packages to all your servers without consuming resources building it locally. So you build it once and you distribute that. And we have the docs repository, which is responsible to keep track of documentation, and also the FreeBSD website. We have the FreeBSD Foundation, which is a non-profit organization that helps the project, but the project doesn't depend on the foundation. They are completely independent. The foundation helps the project with law stuff, like they have lawyers, and lawyers are expensive. Like when I mentioned it, for example, when GPL3 was released, we needed to know like how are we going to be affected by GPL3 if we import new code into the source repository. So we needed lawyers to do that. And the FreeBSD Foundation sponsored that analysis, and they said, okay, you can't import more GPL3 code. You can't import any GPL3 code into the source repository. And when it happened, it was when FreeBSD got stuck with old compiler like the GCC 4.2.1, I think, which was the last version with GPL2. And then we started to move to LLVM Clang. FreeBSD Foundation also advocate the project all around the world, attending conferences, making presentations. This presentation is based on the FreeBSD Foundation one. They borrowed them to developers and said, okay, here is a base, you can use what you want. And they also hire people to work full-time on FreeBSD development, and they sponsor specific developments. Like, oh, let's work to provide like Netlink. Linux used Netlink as a layer to access network stuff, and FreeBSD didn't have that. So they can sponsor things like this. Let's put some people working on that and get the support done. We have a core team, which is a team that coordinates lots of stuff. I'll talk a little later about that. But they are 9 people elected, and they have 2 years terms. They take care of the project in many aspects. We have a mentorship policy. So when you start contributing, you start sending patches to the project. And if you keep sending high quality code, at some point you're going to be punished with a commit bit. So some developer will approach you and say, hey, you're sending good stuff. It's time for you to start taking care of that yourself. So let's make you a committer. So as a committer, you have access to the Git repository. You can make your own changes over there. And for the source repository, core team must approve. So if I'm going to propose someone, I needed to submit an email to the core team and say, I want to propose this person. This person is doing a great job, submitting patches. And this person is a nice person to talk to on the mailing lists, and is responsible and everything, and they are going to vote. If you are accepted, you got a commit bit, and the person that proposed you becomes your mentor. So every change you want to do on the code must be reviewed by and approved by your mentor until the mentor says, okay, this person is ready to fly solo and releases you from the mentorship. Then you are free to do whatever you want on the operating system. And of course, if you are doing big changes, it's nice to discuss that earlier. And so it's a consensus, it's a community. But FreeBSD Foundation will never determine what you do as a developer. You are free to work on whatever you want to work. So here are the teams. I don't think they're all here, but we have a security team which receives notices about security flows and creates all that embargo stuff and take care of that and prepare the patches for the releases. Document team, cluster administration, which are people that take care of the machines we get. Release engineer that takes care of the FreeBSD releases. Ports management for the ports team. And lots of other small teams with different functioning, like postmaster team that takes care of the mail servers, and that's basically like that. Teams of volunteers. So the core team, as I told, there are nine members elected, and every active committer can vote. So every 2 years we replace, people try to do a second term, and usually the core team is usually formed, it's a natural process, but it's usually formed by half by old people and new people. So new blood is always good, and old people can help with to keep the balance. It's nice. They have a secretary. No, it's not voted. They choose a secretary and say, hey, do you want to do this job? Nobody wants to. And if the person accepts, they become secretary. They do administrative things like the commit bits, approving the commit bits and hacks, and they do a strategic coordination, like on conference they start to discuss with the audience what we want for the next major release, like FreeBSD 15 that's going to happen in 2 years. They started discussing that and preparing wiki pages with details to try to attract more people to do that job. And they do, of course, we are talking about people, and there are conflicts, and our team is responsible to try to approach and try to solve those conflicts. It's the most hard part. And we have no benevolent dictators for life. It's the teams are replaced all the time, and the project is never maintained by a single person. Regarding the FreeBSD releases, and that's important for vendors and for companies that want to use that, we respect the POLA, which means we don't do things that are going to cause much changes for users. One good example of that is we have 3 different firewalls available on FreeBSD: IPF, IPFW, and PF. And PF was ported from OpenBSD in the past, and then during the version 4.5 of OpenBSD, I don't remember, they changed completely the syntax of the config files. And then the FreeBSD refused to import that version because it would violate the POLA. And then we started to maintain ourselves our version of PF, which is much better than OpenBSD today. And yes, it's true. OpenBSD still uses a single CPU core for the PF firewall, and FreeBSD is multi-threaded. So yeah, it's much better. And we have major releases every 2 years. So the FreeBSD 14 release cycle already started, and it's going to be released this year, hopefully, until the end of the year. And so here are some examples. The 11th version was released in 2016 and ended the support in 2021. So the releases have a life of 5 years. And point releases are happening during these 5 years. So the FreeBSD 12.4 is the last one for the 12 series, and it's going to die in December 31st this year. And the most stable version is 13, and we are on 13.2 now. And it was firstly released in 2021, and it's going to survive until 2026. This is the way the release cycle happens on FreeBSD project. On source repository, this is the way the branches are organized. We have the main branch, which produces the FreeBSD current. Since Thursday, it became 15. So if you install this branch, you are going to be running FreeBSD 15 current. It's the development version, it's open, and all the developers commit stuff on that branch. So this is where the API and ABI changes happen. Then when we are releasing a new major version, like is happening now, we create a stable / the release number branch. So stable / 14 was created this week, and it is the FreeBSD 14.0 Alpha 3, I think. But it's a stable branch. No commits are made directly on that branch. We always do changes on main first. And then we cherry pick that to the stable branch after some time. So if it's a simple change, you can cherry pick after 3 days, for example. But it's a more important change. Maybe you need 1 month of testing before you bring it to a stable branch. No API ABI changes. So if you build a binary on FreeBSD 12.0, this binary must run on FreeBSD 12.4. It's important. It's important for everybody that consumes that system. So no ABI changes. And when the stable 14 is ready to release 14.0, we create the Relang 14.0 branch from stable 14. And the release happens. After that, only security updates and errata notices are applied on it by the security team, which is the only team that have access to commit on that. And then we create a release called 14.0 P1, P2, P3, P4, just to identify in which version you are. So it's only security fixes. And then the stable 14 keep receiving code, stable code, until it's time to release 14.1. Then a Relang 14.1 is cut from stable 14 again, and the release process happens. And while that, the main changes, the breaking changes are happening on main. Like the 32-bit support is going to be removed for 15. It's going to happen on main, and it's going to happen after 14.0 is released to the public, because now it's not a good time to make such big changes. But we try to do all these big changes in the beginning of the release cycle. Like the beginning of FreeBSD 15 is now. So we try to do the biggest changes now. And then we have time to mature that code. And of course, we try to never break the main branch. And you see Netflix is using that for a long time, and they are confident we don't break it often. So we try to don't break it often.
You don't have a person, I mean, you said that there are multiple committers and you don't have a benevolent dictator, so, but do you have people coordinating these things? I mean, because it's very difficult, I suppose. I mean, it's not only kernel, it's a full operating system, and you have different branches. So is there one person responsible for stable, for instance, or a small group of person?
No.
How that works? I mean, because how these people get consensus on when to cut
when you
things?
do a commit that you want to, we call it MFC yet because it was merged from current in the past, from CVS days. But when you do a commit, when you do a change on main that you plan to MFC, you put a tag on that. MFC after 3 days. And then it's used for you to be notified by email. Hey, you have this commit you would like to MFC. And people review the commits. So we get pre-review on Fabricator. It's not mandatory, but we often use it. But after you push that and say, I'm going to MFC these, people start to reaching, oh, hey, don't do that, because you're going to break that. And people discuss that. And there's a policy like, you broke, you fix. So if you broke the stable branch, you fix it. If you don't fix, any other developer go there and revert that commit.
And the same works for the relang?
No, the relang is only the security team. It's a team. It's not a single person. It's a team. But only security team can commit to relang. Yeah, it's not open to the public because it can't be. Yeah, because the security team is the team that coordinates. Because all this process works out of the cameras. Because when we are talking about there are embargoes and people are not supposed to know about the bug before the fix is in place. So they prepare the binary upgrade, because you can upgrade a running operating system with a small binary patch, and when they announce the patch is ready for download. So it's a very quick process. As I mentioned, the ABI stability is one of the most important items why people use and choose to use FreeBSD. The major release model we have, it was not always this way. FreeBSD 5 was a completely disaster at this point of view, because we have a rock solid FreeBSD 4, and they decided to make so many changes on the version 5. It took like 2 years to stabilize that, and it was a mess. This is the reason Matt Dillon, which was an important guy, left the project and forked Dragonfly BSD, because he didn't agree with the changes at that time. But it was, in the end, it worked, and we learned like we can't do that. And there are so many changes in the same release. So we moved to this release process we have until today, for 2 years for new majors and 5 years for a single version. The business-friendly license, ZFS, which is a file system from the Solaris, and it's feature-rich, and people love it. I love it. I'll try to go fast on the next slide because the time is short. But most kernel features, it's a multi-processing, multi-threaded kernel, as everybody expected in 2023. Architectures. We are POSIX compliant, so if you write code and your code is compliant to POSIX, it's going to build and work on FreeBSD. We have support for many network stack, like IPv4, IPv6, IPX. I don't know if anyone in the room knows what IPX is, but if you know, you're old, definitely old. IPsec, SCTP. FreeBSD was a reference implementation for SCTP in the past. The build system, which is really simple. For the kernel, for example, you have a single text config file, and you just type make build kernel, and that's it. It builds the kernel for you. And for the system, it's the same. You have a big source code, but you type build world, and it builds the system for you. It's really, really easy. I'm not sure how easy it is for you to reproduce a Linux distribution build. Like if you want to build Ubuntu Jammy yourself, all the packages and all the images and everything. I don't know how easy it is to do, but on FreeBSD, you go to the repository, type make release, it creates all the installation images for you. And you can customize that, of course, but it's really easy. So yeah, when you install FreeBSD, you have a complete operating system. You don't need anything else to have a usable system for you. You can install the packages for extra functionalities, but the basic is there. You have an editor, you have a libc, you have a compiler, and then you can start writing code, C code, C++ code for at least. And userland is always in sync with kernel, which is important. So if you create a new network structure on kernel, the developer that did that will need to do the changes on ifconfig, for example, to support that. So if you upgrade FreeBSD to a version from version 12 to 13, you're upgrading the kernel and the userland, and it's going to work. There's no big problems. Other small, nice features. We have robust file system, include the original Unix file system and ZFS. We have dtrace, which is another tool that came from Solaris, Open Solaris. And dtrace is a tool that helps you to profile the system. It helps you to troubleshoot a system in production. So you can see everything that's happening on the system in real time, and you can have fine-grained access to see functions parameters. You can see what parameters functions are receiving right now, and you can see it on kernel and on userland. And you can script that to collect only the data that is important for you. So it's a really nice stuff. We have Jails, which is a lightweight virtualization added to FreeBSD back in the 2000s. Basically, it's comparable to Linux containers. We don't have Docker, but it's compared to Linux containers. You have another system completely separated, and you can separate that on, we have VNet now, so you can separate the network stack completely. It's a completely separate network stack. And we have Beehive, which is compared to KVM on Linux. It's a hypervisor, and you can boot Windows, Linux distributions, other BSDs using that. Capsicum, originally developed by Cambridge University Computer Department. It's a sandbox, and it extends the POSIX API to make it possible for you to have different attributes, security capabilities. You can say like this binary can do that or not, and it's interesting to see. I don't want to talk much about it, just putting the names here. And so, just finishing that. Why use or contribute FreeBSD? Well, it's a really interesting operating system. The source code is not so big when compared, for example, to Linux. Linux is much bigger. So it's a nice operating system for you to learn about systems, to learn about kernel development, and it has a really nice community. It's easy to find people and to talk to people. Some people that helped to develop BSD at Berkeley in the 70s are still around and still contributing with code. You can talk to those people. You can talk to them. They are really easygoing. It's a great operating system to be part of. I am using FreeBSD since 1999, and I am a committer of the FreeBSD ports 3 since 2005, and I'm still around because it's fun. And it helped me to build my career. So it's really nice to get involved with any open source project. But if you want something, if you want to try something new, try FreeBSD. Why not? And if you like it, try to join us. Patches are always welcome. And you have questions?
Any questions?
Yeah, over the packaging system. You said that you basically have link files for each package and you build them on your machine. But let's say you have a Firefox, for example. Do you have a cache if you don't, you just want the application not build it yourself, or do you have to build it?
No. Yeah, the ports tree is used to build packages. So if you want to build packages locally on your system, you can do it. But on FreeBSD we have resources and people working, and they build packages constantly from the ports tree, and those packages are available in binary format. So you can just type package install Firefox, and it's going to install Firefox and all dependencies using binaries from the FreeBSD repositories. You don't need to build it. You can do it, but you don't need to.
And do you have multiple versions on the cache? Like, let's say you have multiple commits that added some change to Firefox. Do you store all those changes?
No.
Or,
No.
so if you want to build an older version, you need to build it yourself.
Yes, or you don't upgrade. Yeah, we have older versions available in other repositories, but only for older FreeBSD versions. Like if you are running 12.4 and you go to the 12.3 repository, maybe we're gonna find an older version of that package. And one great tool about ZFS is boot environments. For example, the loader can be pointed to the ZFS volume, which holds your root partition. So when you're going to upgrade your system, the system and the packages, you can create a new root partition. There is a tool called BECTL for that. You create a new boot environment. You do a chroot inside of that new partition, and you do the upgrade all inside of that. Then you say to the BECTL, try to boot this new volume just once, and if it doesn't work, you return to the older one. Then you reboot. If it works, you activate that as your main boot. If it doesn't work, you remove the power, plug again, and it boots on the old one. It's very nice.
Thank you.
You're welcome.
How does it work about debug packages? Like you want to debug the GDB, for example, you have two kind of packages, one that's released and one is debug version.
For packages?
Yes.
No, for packages we don't have debug packages. For the main stuff on the source repository, we have debug symbols all available for everything. But for packages, we don't have that. It's something we should do, and it's something that I'm involved with the parts management team now, but it's so recently. I still don't know much information about the plans they have, but it's something we should have. And we have GDB available, and we have LLDB too. But only for kernel and base stuff on the source repository.
And how does it work in the service? How does the bugs?
They are stored on a separate directory. You can install them or not. You have knobs to disable what you build. But on the installer, you can choose kernel debug symbols and source debug symbols, and it installs it for you. And when you upgrade the system, it's going to upgrade the debug symbols too. They are kept on a separate directory and loaded by GDB or LLDB or KGDB.
All right.
Do you use RTM or something else?
No, we have our own package version. It's called package PKG.
PKG.
Yeah. It was developed. By a FreeBSD developer called Baptiste Darusson. It's different from, but it does the same. Yeah, it's different. It's yet another package manager.
Okay.
Got a question. You mentioned about the FreeBSD has some instructions about multi-core and OpenBSD relating about single core.
Only on PF, the firewall.
Yes. But I just want to know about this environment, it's operational. If he support a kind of support for HPC developers like CUDA, OpenMP, or even MPI, how is this performance about this situation in HPC?
I don't know, but CUDA is needs some NVIDIA proprietary stuff now.
CUDA needs NVIDIA drivers,
Yeah.
probably not available, but MPI, OpenMP, these are probably available because these are open source libraries.
Yeah, but CUDA requires some NVIDIA stuff. I don't think it works. I heard some people talking about use some GPU pass-through from a Beehive, Linux running on a Beehive virtual machine, but it's not there. Yeah, it's not there.
Okay, any other questions? Thank you very much, Renato.
Thank you.
So we will be back at 2.
Tá, teste. Tá bom o som? Tá aberto o microfone? Pode começar? Okay, let's start. So thanks for joining the presentation. To crash or not to crash, if you do, at least recover fast. Crash, debug, and that part of kernel is very interesting area for me, oddly, because it's broken stuff, right? So I'm Guilherme. I will present now this topic. So for those that don't know me, some people already know me. So I always loved computers since I was a kid. I started programming super early. Then I go to mathematics. I went to a bachelor in applied mathematics, and then a master here in Unicamp, IC. Then I moved to IBM. My first work was IBM Linux Technology Center. So I worked there in kernel, in Power I/O, PowerPC mainly, PCI stuff, PCI 64, etc., and KDump, which we were going to talk a bit soon. Then I moved to Canonical some years later, working in sustain engineering, which is a support team. We worked as a support engineer, last level engineer. So if customers had trouble and anything, we need to debug and provide solutions. And there I worked with Ubuntu, kernel, some user space, and KDump again. And finally, I moved to Igalia recently, which is a worker-owned cooperative. So very interesting place, focused on open source and free software. It's very interesting to work there. I'm working in x86, ButterFS, and a bit of KDump again. Right? So, what is a kernel crash panic? Or panic. Crash and panic are synonyms, right? So Linux is mostly a regular software, right? Written in C, and a bit of Rust recently. And so there are bugs. And when the kernel detects a problem, we call it oops. It's not a panic per se, it's the kernel detecting the problem, right? Some causes of the problem are null pointers, lockups. Null pointers, it's not like the programmer wrote wrong code, like doing new stuff. It's because of concurrency, as SMP, multiple CPUs. So you need locking mechanisms and whatnot. And we have lockups. Lockups, for example, soft lockups. We have interrupts that take a while, and the kernel threads, they get stuck. So it's called soft lockup. The kernel is delaying processing, right? Hard lockups are different, are when you have the same situation, but in interrupt context. So you cannot exit that context. Those situations, you can configure the kernel to panic on that. Panic is an action that is taken when an oops is detected. So oops is an error log and whatnot. Panic is the action that is taken for the kernel. For example, you can reboot in such action. You can collect the data. We're going to mention more about this. Right? Other conditions, out of memory situations, invalid memory. If a driver accesses, for example, pages that they cannot access for some reason, you can have this problem as well. And you have also the bug call, which is very interesting. If a programmer, for example, a kernel model, they consider that a special corner case could not happen. But if that happens, it's completely crazy, shouldn't happen. You can put a bug there. So basically the kernel will force a crash in this situation, right? Oh, you have Caesar keys as well. Caesar keys are a mechanism to induce a panic. If you prefer to induce for testing and whatnot, you can also do that. So that's a portrait of a kernel panic. I usually don't like to put codes in slides because it's a bit difficult to read and whatnot. I try to make it visible here, like black on white. So this is a portrait. Panic can vary. The log, of course, can vary based on the cause of the panic and whatnot. So in this case, worth to take a look, especially in the bold lines. Kernel, this case was a null pointer reference, right? Page faults. You CPF there, which it's an x86 exception. Exception may vary based on different architectures. We have oops, the oops entry, and a call trace. You can see a call trace that helps to understand how it failed. The call trace of the functions that reach the failure.
RIP is a register in x86 that shows the function that failed specifically. The problem in this case was DRM SCAD FINI. It was a real case. So we debugged that. It was wrong stuff there, and we managed to fix. So this is what it looks like. We can see the kernel version. In this specific one is 6.1 dash Valve. And Valve is the company, the gaming company. I'll reach to there, but this presentation is related with gaming as well. Panics on game devices. So how does it happen? So the kernel detects the problem, as I said, and show that kind of logs. There are some CCTLs and some tunings you can configure to force the panic. So oops is detected. You can live with the oops, right, if you want. But you can trigger the panic. And the goal for triggering the panic is to recover the system, because system in oops stage is not really reliable. Some modules, some parts are broken, right? So you don't know the implications of that. So you might want to reboot in this case. Some tunings are, for example, panic on out-of-memory situations, on lockups, on hand tasks. So you can configure the kernel to panic in those situations. The panic condition is very abrupt and arch-dependent. So as I mentioned in the log, the registers of that log are x86, but RISC-V or ARM are different, depending on the architecture. Things change. This is an oversimplified code flow of the panic, right? So the panic process involves disable our IRQ, preemption, which is the scheduling of threads and whatnot, and then dump the stack. If you configure kdump, which I'll mention later, I needed to mention here because of the flow, but it's kind of a chicken or egg situation. Because if I mention kdump here, I didn't talk about that, but if I don't mention, I couldn't present this diagram. So if you manage to configure kdump, you go to crash kexec and kexec code. If not, we disable the other CPUs. We go to panic notifiers and kmessage dump, which I'll also talk later. And eventually reboot the machine, if that's configured. Arch code to reboot the machine. Right? So, what can we do? This is the main topic here. We can reboot and pretend nothing happened, right? Or we can use this opportunity to collect data, because we're broken. So if we can collect the data, it's very interesting in a panic. We have some ways of doing that. VM core is a memory image of the broken kernel. Is the kdump mechanism, which I'll go through more. And the message is the kernel log, right? So you can collect only the kernel log or the VM core and the kernel log as well. We also can use console for that, net or serial consoles. For example, if you have a server, usually have serial output. You can collect those logs based on pictures, or you can dump through screen or tmux or a mechanism like that. Net console is another thing in the kernel, but I don't really like that, because basically is configure network and a network console, but if the kernel is broken in oops or panic, network might not be reliable, so it's not really great way of doing that. And we have kdump store, which are the main topics here, and debuggers. For example, xmon was a debugger in RPC. So if the kernel reached that condition, you can check stuff that, like GB-like interface. So you can dump your register and whatnot, right? KGDB is also a debugger, but I don't really know that. Never used KGDB before. So the first method is collecting all the data, kdump. So kdump works like this. Kexec is a technology that the kernel will jump to another kernel. You not go to the BIOS, for example, the firmware, right? So this technology allows, for example, fast reboot and the kdump mechanism, which is kdump, kexec, a crash kernel, which is a kernel that collects the memory of the first kernel that's broken. So it's a smart idea. You reserve some memory, put a kernel there, like a reserve kernel. Then if the kernel breaks, you jump to this new kernel. It's a new boot, like there's user space and whatnot, tools, to read the memory of the broken kernel and save that, for example, in a storage or through network. You can use SSH to save that information, right? And VM core, as I said, is the memory of the broken kernel. The advantage of that is that the memory dump can be inspected later. Here's some more advantages. right? You can do post-mortem analysis. That's the main use of that. So if you have the memory of the other, the broken kernel, you can inspect that in a GDB-like tool called Crash. You can send to somebody else to examine for you. For example, some company that does this work. This was kind of a work I did in Canonical. So customers sent kdumps for me. So I needed to take a look in the logs and figure what's going on, right? Advantage is also you can collect the logs through network, right? But there are some disadvantages, some challenges of kdump, a bunch of them, in fact. So the first one is that you require a preserved memory area to this other kernel, the kdump kernel, as we call. And this is more and more lately. For example, actually, 200 megabytes is the minimum today. So if you have a small machine or embedded device or anything, 200 megabytes pre-reserved is not great, right? Crash kernel, there are some risks also in the kdump. Broken kernel shutdown. It's not really a risk for kdump because it's a risk of the panic situation, right? The kernel can break in the situation. You cannot bring the other kernel, cannot KSEC. But if you do KSEC, there are other challenges like crash kernel, booting problems, or the data collection phase. The KSEC kernel, when booting, it will need to restart the devices, for example, PCI devices. And PCI resets, as I said here, is a nightmare. It's very difficult because it's arch dependent. PowerPC, for example, has some tricks to do that in firmware. So kernel can communicate with the firmware and reset the devices. But x86 does not have that, right? So the device cannot work and break the process of boot of this kdump kernel. And I'll tell about a true story about this soon. Next slide. Other problems of kdump, no graphics on kdump, and long boot delay. So basically, the KSEC kernel is simple. So you usually don't start drivers, graphic drivers. So you don't have output. So user does not know what's going on, right? It can incur some long boot delays. And I put there film port compatibility is not really a flaw of kdump, but happens that the tool that collects the memory of the broken kernel is called make-dump file. You need to adjust that tool to new versions of the kernel. So you need to keep track of that, and it must be updated, right? So it's more or less a requirement of the distro you are using usually, right? If people have questions, please feel free to do that now. Is interesting as well. So a true case, interrupt storm. As I mentioned, the PCI resets are very arch dependent. PowerPC has these firmware calls you can do to reset the devices, but x86 does not have. So this case was like we worked in a customer situation in which the customer was using an Intel network card through the PDK. The PDK is user space driver. Instead of using the kernel stack, it uses this user space stuff. And the customer wrote a module to the PDK to collect statistics on the device. Okay, so eventually we received the support call that the machine was not booting in the kdump kernel. And the reason of that was that this DPDK module was triggering a bad condition on the firmware of the device and creating a storm of interrupts. The device was interrupting like continuously. So the kernel just cannot continue. So we can configure kdump. Kdump is going to boot, right? But then during the boot process, when the interrupt controller is initialized, there is already a bunch of interrupts there. So the kdump kernel also cannot boot. The same as the bad kernel, the old kernel that was broken. So how to debug this? It was very complex, and in the end, the solution was to use a mechanism x86 to write some early code in entry points of x86 to perform a clear of the MSIs, which are the interrupts of the device. And this acted as a reset for this, and then the kdump was made possible. There is a link here for the discussion. It's an interesting discussion, but it was not accepted, unfortunately, because the PCI maintainer complained that this early infrastructure is too restrictive. It's only for the bus 0 of PCI, but new servers has more PCI devices, more buses. It's something new. So since it was a bit limited, he preferred not to accept that. I disagree a bit, but I may get back to it eventually.
So is this an x86 only problem?
What problem, you mean?
The PCI storm?
The PCI storm, no, it can happen in other machines. But for example, a PowerPC has the PCI reset stuff. The skip boot, remember skip boot? So you can kernel, during the KExec process of the kdump in the PowerPC, there's a call to skip boot firmware that resets all the devices and put that in the original state. It's the same that happens in x86 during the regular boot. The BIOS does this. Problem is, in x86, there's no API for that. It's like vendor dependent. The BIOS does this, so KExec has no access for this, right? So it might happen in other architectures. So
I mean, sorry,
Go ahead.
interrupt. I have a question about the previous slide, actually. You
Previous.
said that you have to preserve memory.
Yeah,
How do you know how much memory you need to reserve? Because I remember that was quite the challenge back in the IBM days to decide how much memory you should reserve to kdump for the memory, right?
exactly. This is a big, it is a great question because it's a big problem, and the customers in Canonical also faced that problem of reserving the memory. So you don't know, basically you don't know. The way people usually do is to test. Remember I mentioned CSRQ, so induce a panic and test. But there are other ways. I worked in Canonical in a memory estimator for that. So it's like, it checks early in the boot time how much memory was consumed, do some heuristics with number of CPUs, because kdump kernel usually it's a mono CPU kernel, right? Only a single CPU. And I figured out when I finished working on this estimator that Fedora has a similar tool, but Fedora 1 requires a reboot. So you configure the tool to reboot and perform the analysis, and then it tells you, oh, should save, I don't know, 200 megabytes, for example. But usually it's done manually. Is the way that's usually done. So it can happen in all the distros, and well, that's very difficult. The estimator, by the way, was not merged because Debian kdump tools maintainers are asking some stuff, and I didn't finish that. Right. So as mentioned here, we have a bunch of challenges on kdump. So there is another alternative, which is called pstore. So pstore is very interesting because it's a lightweight mechanism. The difference from kdump is that kdump requires booting another kernel. So you can exec another kernel to collect the memory of the first one, right? pstore does not work like this. In the final phase of the broken kernel, you dump the kernel log, the pstore technology, the front ends dump the kernel log to some backend. You have multiple backends and multiple front ends. So for example, one combination that we used in our use case here, it's rumoops. So basically we configure this tiny portion of the memory of the machine that is reserved, not used by the kernel. So when you have the situation, you dump the kernel log there and reboot the machine. So it's quite fast because it's just a write into some memory and reboot. You don't require another full reboot. And you have more front ends, which is very interesting for multiple debug approaches. You can dump, for example, the ftrace log to pstore, which is the Linux tracing mechanism. I remember Garga mentioned dtrace in FreeBSD. And in Linux, ftraces are similar to detect functions and that's running in the arguments and whatnot. You can dump the console, you can dump user space. It's called pmessage, this front end. So some user space too can dump to pstore as well. And as for the backends, you have RAM UEFI. So you basically dump to UEFI variable. The problem is that it's a bit small, right? But you can, a small the message fits there. ACPI Erst, which is another area for ACPI is the protocol of the BIOS in x86, so there is an error facility there. And even a block device, recently it was added. If you have a block device, you want to fully use that for pstore, it's possible as well, right? So, the benefits of pstore. It's kind of, it's very fast because it's in the end part of the panic that this process happens, right? You don't need to bootstrap a new kernel. It's more secure, less prone to failures. Although I put citation in it because the kernel is in a panic state. So of course it can be so broken that it's unable to do the pstore. But usually it's very safe. It usually works, right? It does not require KExec support and can be used to another, as I said, to another front ends like ftrace and whatnot. For me, the best advantage is that you don't require to keep 200 megabytes stuck there for nothing, because you should not panic usually. It's a rare condition. So basically block that amount of memory in all boots, right? with PSTOR, you don't do this. You don't need that if you are using RAM. If you're using UEFI, for example, you need no memory at all because UEFI has this storage area. So these are the main advantages of PSTOR.
Just one question.
Sure.
Regarding the KDump, where does it save the crash file?
It's a good question. You can save, it's very flexible usually, because it's a new kernel that put it there. It's basically, you can think it's a minimal distro that puts. So for example, you can configure network there and dump through SSH into another machine. You can dump in the storage, a different storage like USB.
The storage can be in a broken state too.
Exactly. That's one of the big problems. So what we did in the past, in IBM times, IBM machines had multiple storages. So we reserved one storage for that. Because it's a different driver. Because imagine you have, I don't know, AHCI, which is the usual ID devices for most computers. So if this driver is broken and causes the panic, it might put the device, the PCI device, in a really bad state. So when the KDump will start without the PCI reset, device is broken. Guess what happens?
Yeah.
Right? You cannot collect the data and the machine might be stuck. Which is even worse. The user does not know what's happening because there is no output, no graphical output, so it's way trickier. And the PSTOR, you have the specific backends, right? So it's more safe, right? So these are the benefits, the challenges of PSTOR. The main one, obviously, you are not collecting the full VM core, the full memory image, so you will lose data. But for most cases, the message is enough to understand the problem. And you can circumvent that with the panic print option. So you can print more stuff. For example, you can print the states of the user space processes, the memory, and the states of the memory, OM or whatnot, timers, the locks that are taken. So it's a very big message full of question.
Yes, to use it, basically it's just like KDump, you change the kernel command line. How do I set my system to use
PSTOR? I'm going to talk about PSTOR setting, but the problem is that there's no tool to do this. KDump usually has a tool, like KDump tools. PSTOR, now there's a new tool, but I'll mention that soon, okay? So you can circumvent that disadvantage, right? And another problem of the PSTOR is that it runs after the panic notifiers. Panic notifiers works like this. When the kernel panics, there's a list that any driver, any portion of the kernel can add an entry there. What does it mean? That when it panics, this list is run and functions callbacks are called based on devices that register such function. So people can do whatever they want during the panic time. So a lot of problems can happen there. For example, remember the diagram, we disable other CPUs, we disable IRQs. So imagine some panic notifier takes a lock, a mutex. So it sleeps, nobody will wake up ever. It's there, it's stuck. So it's a very dangerous infrastructure that must be used wisely. And this link I put now here is a link to a discussion because this is a big work we are trying to refactor those panic notifiers to be more reliable, more safe, getting the panic notifiers that are currently in use, make them safe to run during the panic really, and splitting some lists. But for now, it's not merged. It's a work in progress. So there's this risk, right? KDump runs usually before the panic notifiers. Right on when the panic happens, it jumps to the new kernel, right?
Just a couple of questions.
Sure.
How new is PSTOR compared to KDump? And if I understand you're saying it's quite new, so it's KDump is still a lot more utilized than PSTOR nowadays, or is it going to change?
It's a good question because none of them are new. Both are kind of old. But for some reason, I don't understand, people does not know PSTOR. They just don't like PSTOR. I guess it's because KDump get more tools. I hope to change that. I hope that it changes. We can spread the word about the religion of PSTOR because KDump is full of problems. It's not full of problems. It's a good technology, but it's a thing like a lot of times I use KDump. I needed to debug KDump. So it's basically, you want a mechanism to debug the kernel, but let's first debug the mechanism, right? And PSTOR, I don't know, I tried that, recently, I'm going to, it is bad that it's the next slide, but I'll advance a bit. There's a new tool for Arch Linux that uses pstore. And when I tried first time to use the pstore, it works flawlessly. Super simple. So both are kind of standard, not so new tools, but pstore is not really known for the public. And distros, they didn't invest in creating a tool for that. So until now.
So yeah, but I mean, you know, how useful is pstore to debug real world problems, right? Because I remember, I remember that even with kdump, sometimes the information that you collect in the VM core is not enough to debug a problem, right? Sometimes you have to reproduce the same problem multiple times, generate multiple VM cores to really understand what is going on. And you have all the kernel memory dumped there. In pstore, you don't have all this information. So is this really useful? I mean, maybe that's why distros are investing much more on kdump, right? Because they find it more useful. So in your experience, I mean, is pstore really useful to help with that? Because it doesn't seem to have enough information, maybe, I don't know.
Yeah, depends on the problem, right? In fact, this is a trade-off. And kdump, we mentioned here, that it collects whole memory, but device memory is not collected. So for example, the MMIO region, the bars of a device are not collected. User space data are not collected as well, because remember I mentioned makedump file, the tool that collects the logs. Imagine a machine you have 64 gigabytes. It's too much, right? So it cuts parts of the memory. It cuts user space, it cuts free pages, some stuff. So it's not really full, but okay, it's fair. It's a bunch of memory to debug and go through structures and whatnot and determine. So it's a better tool, but imagine like this, you have a pstore set in all machines in the world. It's just an ideal scenario. So you have a server, like Sentry, telemetry, those kind of technologies that I really don't understand. You submit all of those logs there. So you have statistics about that. You can correlate stuff and say, oh, this kind of crash, because you see IRP. IRP is the pointer to the function that failed. Excluding the offset, because offset, of course, changes according to the build and whatnot compiler. But you just isolate the function, you can have suddenly a statistics of that function is broken. And it's enough information at least to start to configure kdump if you need more data. So we can consider that tier 1. But it's in most cases is good enough to this example I put there, the portrait of the kernel panic. I just used the message to debug. I didn't use kdump at all to collect. Because kdump is, you need to navigate in the structures, so it's not easy. It's not like comfortable to do. You only do that when it's less resource. You really need to do this. pstore, eventually you look at that and you go to the code and the function, you read the code, I see the problem. You know, it's very useful, in fact, for some kind of bugs. But I think you are right. People can think about that and say, let me configure kdump because it's better. It collects more data. But not always the more is the best, right? Because you have a bunch of risks, as we mentioned. So, okay, challenges of pstore and available tools. This is interesting. As I mentioned, that we don't have tools for pstore, at least that I know. Maybe there is some, of course, GitHub, people wrote some tools. But for kdump, we have plenty of tools. Notice kdump and pstore are kernel technologies, so you need the user space counterpart. How does that work? To configure kdump, you need to configure the kernel command line to reserve that memory. Then you put a new kernel, right, the minimal one. And the minimal one must have the tooling to collect and save that. So it's a bunch of scripts and whatnot, it's all automatic. So we have plenty of tools. For dev in Ubuntu is kdump tools. The name of the tool is kdump tools. But it's the same tool. But for Ubuntu, there are some patches and whatnot. For Fedora is kexec tools, which includes the kdump scripts. And for SUSE, it uses the YAST. And I remember I think some people remember YAST or people that use SUSE, right? So, no, because of the MTC, yes, the MTC we use YAST a bit, but I stopped to work at SUSE. Some people might be in the same condition as I am, so they forgot about SUSE. And so, okay, for VM core analysis, we have some tools, Crash and Dragon. Crash is a standard one. Everybody, I guess, at one point heard about Crash and whatnot. So Crash tool is good. It's like a GDB. It includes GDB in the code. It's a tarball of an old GDB. You cannot update. inside the code of the crash. So, but the people complain a bit about crash because it's not great for programmatic analysis, for scripting. So it's not friendly for that. You can do that, but it's super difficult. So recently they created Dragon. I guess Meta, Facebook created this too. So it's Python based. You can write some Python scripts and navigate through structure. So it's very friendly and powerful as well. But notice I didn't mention Arch Linux, right? And Arch Linux has no tool, no official tool. There's the wiki. Arch wiki is really great, but it shows all manual processes to configure GitHub. But then we're going to suddenly change subjects to a Linux game console. Yeah, there is one. This one is called Steam Deck from Valve. I guess some people here heard about that as well. And this is the origin of my work recently with pStore. Igalia is working with Valve in this console. I am assigned to work in the crash parts of this. And so it's a very powerful hardware. You see that there is a custom 8-thread AMD GPU, 16 gig of RAM, 3 models of storage, really fast device. It's really good to use. And guess what? SteamOS 3, they have a distro. And this distro is basically Arch Linux, right? With some specific stuff for gaming, like GameScope, which is a compositor, and or KDE. If you want to go to desktop mode, you can use KDE. And there's a bunch of. It's very interesting how gaming is improving a lot of stuff because it's a very complex to run games in Linux. Either you can ask people to report that stuff to Linux, which is difficult, or you can emulate APIs. And that's the approach Valve recently took that allowed DEC to exist. They use Proton now, which is Wine, based on Wine, some modifications to emulate the API for Windows. They use DXVK, which it's a Vulkan emulator to DirectX calls. So it's a big step there to make it work. And so the SteamOS 3 is basically an Arch Linux with this layer for gaming, and Arch has no tool for collecting crashes. So what happens is that we have kdumpst, a new tool. And the name is just a joke because it's a superlative, it's better than kdump. In PST, it's pStore, right? So it's a tool that includes the pStore. This tool is shell script as well. It supports grub, supports 2 init systems, Dracut and initcpio. For those that work with Arch or know more about this, initcpio is the default. But for some reason that nobody could answer, SteamOS 3 was using Dracut. So when I wrote this tool, I needed to make it work with Dracut. As soon as I finished the tool, they changed to initcpio. And it was good. No, it's real story. And it was good because now I can support both. I need to support both because we have versions in both stuff. So having support for initcpio may make it a generic tool for Arch Linux, right? And the big differential for kdumpst is that it defaults to pStore. And so my first attempt to pStore in the Steam Deck was great because it works like a charm. And I'm using RAM, right, RAM backend. And checking the RAM buffers in the Steam Deck, I noticed that for some alignment reasons, the kernel was ignoring 16 megabytes. Was there, not used it. So I already have the memory. I didn't need to reserve and whatnot. You asked me how we can configure pStore. In this case, it was really simple to configure pStore. We can run the module removes with some parameters. You can put the kdumpst can do that automatically for you. But basically, you need to put an address, the memory, the size of the memory, the size of the buffer. And I already have the memory, right? But imagine you don't have the memory. The memory all consumed. So you want to reserve some stuff. Some portion of the memory. There is no current way in the kernel to do that easily. The way I do when I need to test in a VM and whatnot is to use the mem parameter to reduce the memory of the kernel. Mem equals, so is 4 gig machine, I can put mem equals 3.8 gigabytes. So I reserve a bit 20 megabytes there, something 3.88, something, like I reserve. But it's not great. So this is one thing we have in the plans to work, to improve that. But so far, the tool works with RumOps, which is the RAM backend, and we have plans to make it work with UEFI as well, because it's useful. Also, not only group. Right now it's group only, but we want to support unikernels or UEFI directed boot. because it's more is used today, right? The tool also customize CCTLs, the crash kernel, because you can opt to use kdump. I prefer kdump, I can collect vimcore, okay. And if you configure crash kernel parameter, it's present on the SteamOS as the DEX crash collecting tool, default. Previous version, the initial version, also submitted the logs to Valve servers, to those Sentry telemetry stuff that I mentioned. But we removed that from the tool because it does not belong, right? It's like overriding the tool with this functionality that does not belong there. So now there is another tool to do this. It's a SteamOS log submitter, working for a different person that collects the kdump data and sends it to Valve, right? So I welcome you, Arch Linux users, to try this. It would be nice to have feedback. And let's see here. Okay, the missing pieces. I mentioned a bit about the panic notifiers, right? Which are risky, and we have a work in progress about this. We want to split that in multiple lists, not only one single list. For example, Azure or Google Cloud, they require the panic notifiers for kdump because they have a VM, the VM panics. You need to inform some stuff to the hypervisor, and it uses panic notifiers for that, so it's essential to have it. If you don't have kdump, it does not work. But others are more or less, like some devices that dump, there are some notifiers that goes to a device and dumps a lot of registers and whatnot, so you don't really want that by default, right? So right now you have a parameter that you can say kdump before or after the panic notifiers. It's like a Boolean. Either you can exclude all the panic notifiers or you can include all of them. Not great. We want to split that more interestingly. So some list is more mandatory for kdump, let's do it. Some list is more informational. You enable that if you want more information. For example, for pstore. In the case of pstore, you could enable that second list to dump more stuff in the kernel and have more information. And there are the final list, which is like, wow, this is just a lot of MISC stuff that put that in the list. So the work is a bit polemic because kernel panic is an area that there is no maintainer for this in the kernel. It's like Andro maintains, Andro AKPM, because it maintains everything that doesn't have a proper maintainer. So it's like nobody loves this area. So when you send a patch, it's very difficult to get feedback and need to ping multiple times. So it's a work in progress. But we hope to finish that. As I mentioned to you, the parameter for improving the RAM reservation would be nice to have. I tried to use crash kernel for this. Crash kernel is the kdump parameter, and it works. I can use crash kernel, reserve a bit of memory, and configure pstore to use that memory. But what if the user wants both for some reason? They might want pstore, and if pstore succeeds and kdump fails, at least you have some logs. If I do this, crash kernel is not enough because crash kernel is the area for the kdump. So I need a new parameter, probably. I'll take a look on that, and it could be Arch specific because it's really early in the boot that we need to reserve that kind of memory that is out of the memory allocator. Some more missing pieces in the kdump word and panic word. Graphic output. Graphic output is really difficult. There was a thread in the DRM list recently, like 2 years ago, about showing a logo or something like that during that time. But the thread died because it's very difficult to use GPUs. GPUs are very complex devices, and they do interrupts for everything. So you disable interrupts in panic. So how can you work with GPUs? So it's not great. One idea would be to restore the frame buffer. When the BIOS inits the machine, we have like a simple mode called frame buffer, right? Then the device, the AMD GPU driver or NVIDIA, the big drivers, they reprogram the GPU to be really powerful and use all the power. And this is difficult. You can't usually unprogram that back to the frame buffer. There is no infrastructure for that. If we can work on this, would be nice. We can restore the frame buffer capability, right? But I'm considering another approach that I think it's easier for the deck at least, which is an UEFI panic notifier. I was talking about panic notifier. So we will have a new panic notifier that notifies just one bit in the UEFI, a panic happened, lightweight, right? And then the BIOS can plot different in its stages. And the Steam Deck is very nice use case for that because it's custom. We are in control of the firmware. We can put whatever we want. And if we can make it work, the link is for the patches. The patches exist and it work, but maintainer complained a bit that it's not really useful. So I'm planning to make that work on deck and show to maintainer, see, we are using that in the field. So try to convince there is use for that. And since we control the firmware, we can plot different stuff. We can use different logos. And that would be interesting because it would be the first device that has this capability. I don't know if, I honestly know if there's any other desktop that prints stuff during the panic. So the Steam Deck would be one of the first, or the first. More like Nintendo Switch, if you use other consoles and they break, there is some logo and whatnot. It's beautiful, right? So Steam Deck is screwed in this respect because it just reboots. So we hope to change that. PCI reset, reliable PCI resets for KDump. It's like wishful thinking. I would like to fix that. We have the patches there, but it's very difficult to fix. There is no perfect solution. I received feedback to use IOMMIU for this, instead of using the early PCI ancestors to restart, clear MSIs and whatnot. Use MMIO, but then I responded, what if we don't use MMIO? This configured, oh, so this case doesn't work. So basically, it's a bunch of corner cases. We need to cover most of them to have more reliable PCI resets. And to add on that, I don't know much of other architectures than Power or x86. Like RISC-V is the new architecture here, some trendy stuff. I don't know how it works there. I need to test PCI resets, but it's interesting stuff to improve. And finally, we have the maintainer's communication awareness, which I think is one of the big issues with pStore and KDump Word and Panic and whatnot. I work in the estimator, as I mentioned to Leo, without knowing the other estimator from Fedora. There is no single community. Everybody's spread. So it's not great. I really hope we could have a more centered community about this. I don't know how to make it work, but how to propose that. Recently, there is a group of people, the Dragon maintainer, created a mailing list and a group of discussion about debugging stuff. I'm participating on that and hope more people can participate and we make more a community of KDump people, right? Instead of spread. So that's it. Mostly, I hope we can, you can now see a bit more how the bank works under the hood and whatnot. Multiple ways of collecting data with trade-offs. It's an area full of trade-offs. There is no perfect solution. You need to choose your battles. Like, I prefer more data, I prefer more reliability, right? Things to improve, we have a bunch of them. And finally, I really appreciate the effort of Valve and the Linux gaming community in improving stuff that it wasn't expected to improve, like Crash. You don't expect that gamers are improving Crash, which is so rare, but it's happening, right? So it's very good. That's it. Thanks for your attention, and feel free to ask questions and whatnot. Thanks.
So does Valve, does Steam Deck reports the errors?
I don't know. I don't know. You know, because the Sentry stuff is work in progress for their side as well. So they might receive stuff, but I don't know how it's going. The deck has only 1 year. They usually call Valve time some stuff. It's like the time that Valve takes to do some stuff. I don't really know why they use this terminology, but sometimes now this new tool that are being used to collect logs collect more stuff. It collects not only crashes, but GPU hangs or some user space stuff they configure to have a bunch of collectors. So I guess now the thing is gonna be more used in the field.
Yeah, I was just wondering. I think that maybe KDump is more popular because servers. The way I see it, at least, servers were what really pushed Linux development in the past 20 years, right? And companies are extremely picky and sensible around crashes because they usually run critical stuff on servers, right? So they don't want the server to crash. And if it crashes, they usually want you to find out what is going on the first time, right? So if you take a look, for instance, mainframes, they have not only KDUP, but they have a bunch of information that is collected from the firmware, because ideally, at least they say that they would not require a customer to reproduce an issue to debug it. It's more or less prohibited in the mainframe world, right? On other server architectures, I mean, this is more common, right? Whenever customer hits a crash, you ask, oh, what was happening? Let's try to reproduce. And sometimes some customers are more flexible, right? Now, if you go to, more embedded-like devices for end customers instead of companies, right? I think people are usually much more or much less concerned about crashes, right? I mean, what's going to be impacted in this case? It will be the game, right? But
yeah.
In theory, nobody's losing money or something like that, right? In theory. So maybe that's why these tools were not developed. These more simple tools, right, were not developed because... Anyway, I'm just wondering. Yeah.
No, makes sense. But on the other side, I guess, since it's so cheap to enable pStore, so simple, we should enable that. And if people want to enable KDUP, great, enable as well. But if not, we at least have pStore.
Yep.
But RAMOOPS as a kind of a last general form of pStore. So pStore was written after RAMOOPS. We had RAMOOPS before, right? And both Chrome OS and Android use that. And so I think they have their own issues. And one of the problems that I see with RAMOOPS, when I was very classy, because since pStore has been developed and now we have Unify and ACPI, I was expecting that you would tell us that you were using those, not RAMOOPS, because when you reset the system, how do you ensure that the RAM is still there?
It's a good question.
And also you have the configured RAMOOPS has all challenges because you have all the boot chain, and how do you ensure that that boot chain is not going to touch that RAM?
I can't ensure that. Really, it's a problem.
Yeah, usually the boot chain doesn't care, right? I'm the first one to run, so...
Yeah, they can mess with the memory. Yeah, you're right. But my limited experience with the DEC and one personal computer, I have x86, the memory is untouched. And the reason for that is that because I guess retraining the memory, we can retrain. You can ask the BIOS to retrain the memory, and that will lose the content. DEC has you can hold some buttons and do some stuff and we retrain the memory. But by default, I guess to speed up the process, they are not doing that. And I'm kind of an advocate of pStore, but not the RAM one. The RAM one is what we use to DEC. It works there, and we have control of the hardware. So we know that it's not resetting the RAM. But for general case, as I'm saying, that's an ideal world. We have a computer with that enabled. Well, it would be a different backend. For example, UEFI. Because usually the message is not so big. And it's compressed, right? It's compressed. So, I don't know, 100 kbytes is enough. And maybe UEFI has this storage.
I've seen some device trees that have the RAMOOPS
embedded word.
So at least parts of the boot chain is aware of that configuration. So you do, for example, do not touch it.
I agree. It's very common. I forgot to mention, it was in the slides, but I forgot to mention. It's used in Chromebooks, but it's very widespread in the ARM world because of device trees. They select a piece of RAM in the device tree, small stuff to RAMOOPS. So it's very common there. It's not common, I guess, in servers and desktop. This is the word that people don't know much about pStore. But for embedded, as you said, RAMOOPS is even precedes the concept of the pStore. It was a single backend there. Right.
Well, in servers and desktops, they are ACPI based.
Yeah.
Usually, right? They are not.
Don't have device tree. Yeah. Exactly. More questions.
As a graphics developer, I think about GPU crashes. We have some sort of information in KDUP and pStore about GPUs, or we have other tools for GPU crashes.
GPU resets, it's very dependent of the GPU. I will talk about AMD GPU because it's off the deck and it's open source. Yeah, NVIDIA no, but we don't know anything about NVIDIA. So for AMD GPU, we have the resets. there are two stuff here. We can have the GPU reset that does not imply an oops. Oops is a bad condition in the kernel. But eventually, the DRM model is based on user space drivers, right? I don't know much about DRM, but the Mesa stuff. So those drivers, those user space, can break the GPU. Like do some stuff that's not great. So the GPU itself is going to reset, but does not affect the rest of the kernel. So there's no panic on DRM break or something like that, some CCTL. So basically, unless this driver breaks in a way that triggers an oops and reboots the machine or causes the panic, basically we won't see the message. And the information is available there. What the driver wants to make it available, right? As per my understanding in the GPU, which is not so much, but the driver does not show many important things there because there's a variability of hardware. It's very difficult to show this information. So GPU is kind of a very difficult area to debug, unfortunately. Sure.
I do talk about the configuring and developing these tools. I was wondering how much of knowledge you have to have about other areas of kernel. How deep has to be your knowledge to develop the tools to be tracing the other kernel you mentioned?
I mean, pstore, kdump to develop those tools?
No. About the other areas of kernel, like, I don't know, how much do you have to know about the GPU area and RAM and CPU drivers and other parts of kernel to be able to contribute to those tools for debugging?
I guess not much, because, well, depends. If you want to investigate a problem, like you're using the tools to debugging specifically, you must have some knowledge or study, because it's very difficult to have horizontal knowledge in the kernel or areas and know everything. It's not feasible, basically. It's very difficult. So what we do is we start to investigate an area once we have a problem. We have a problem there, like, for example, I'm not a DRM person, but I resolved this bug I showed here. How? I looked the code and found the problem there, right? But to contribute to the debugging tools like kdumps and whatnot, you don't need much knowledge of the kernel code, but you need knowledge of the kernel technologies, like parameters, like crash kernel parameters. But it's easier. You can read documentation and get, so it's not much necessary to deep dive in the kernel code for this. Sure.
And how should I deal with microkernels in order to improve, to detect some bugs or fix it with embedded device example? Should we use, is there any tips to use sometimes kdump or even pstore? Considering that we have a limited area of memory.
That's the reason, I guess, pstore is so used in the embedded world, because of the limitations. Embedded is super dependent, of course, on the embedded. There are some new stuff like Ampere machine, it's ARM. It's not even embedded at all. I think it's server ARM, right? But usually people use pstore, collect the data in the message and whatnot, and don't use kdump, as far as I know. We have good embedded people here that work with Leonardo and ARM. I don't know if you have some expertise on kdump embedded.
I'm the server guy at Leonardo.
Yeah. And it's difficult because of the firmware. I have a board there, Enforce board it's called, and it's Qualcomm. And I tried KZAC there, it fails. It fails because it doesn't support KZAC, because the firmware think it's a security flaw or something like that. Embedded is very complicated, it's very ad hoc. It's my feeling, my personal feeling. It's a bit ad hoc. Every vendor does whatever they like. Qualcomm has a firmware stack, own tools, on bootloaders, and so very difficult to deal with KZAC, which is an advantage for pstore because you don't need the KZAC. You don't need to bootstrap a new kernel, but you have limited tooling for that, limited logs, and you cannot collect the memory, so it's a trade-off, right?
Yeah, that's unfortunately true. I mean, the embedded environment is very vendor specific, right? Mm-hmm. I mean, ARM has an initiative called System Ready, which is basically trying to build standards for devices, ARM platforms in general. This is started with servers. They used to have server ready standard in the past. And now this was transformed into System Ready, and you have System Ready SR for servers, and you have System Ready IR for embedded devices. You have multiple different tiers of standards. But I see that on the server side, it's quite easy to get traction on the vendors, and they usually want to be compliant because, you know, cloud providers, they all want things that are standard because they want to easily substitute one vendor by the other. But when it comes to the embedded world, there is a huge resistance in being compliant with the standards yet. I mean, I think this is going to change. And I know that RISC-V has similar issues as well already. And they are also trying to figure out a way to, you know, to change that. Because if you have fragmentation, it's much more difficult to build an ecosystem, for instance.
Cool. Yeah. I hope it changes. We have more standard.
So we don't have more time. If you have more questions, you can get
Please
to Guilherme.
Yes.
All right. Thank you very much again.
Thank you.
Hello everyone. Today I will be talking about improving Linux for real-time workloads. I will start the presentation with some basic concepts on real-time, and then part 2 we'll be talking about things that are already in Linux that can and improve the real-time behavior of the operating system. And the part 3 is something that I'm currently working on, but I will say that whenever the time is ready. Well, the classic who am I slide. My name is Leonardo Brás Soares Passos. I work at Red Hat at Verteam. I do some work with Linux kernel. One of that is improving it for real time, which is this presentation about. I also work with some RISC-V code, ARC-specific code, but as a side quest. And I also do some improvements with live migration. That's my main job, to be honest. You can find me at my handle Leo Brás, at GitLab, GitHub, or at redhat.com whenever you need to talk about something. Well, part one, the basic stuff. I will introduce the basic of real time and what is it. I can't just assume everybody knows that because it's not very used, very spread. Well, these are some definitions you can find at Wikipedia. Real time is honestly, I like this one better. Real time is about having a request or something like that and replying in a defined time limit. After you pass the time limit, bad things happen. So the idea is to try your best to stay at this time limit, which are called deadlines. Well, why does that matter? There are some workloads that need that. You need that your reply to a request happen in like some limited time. There are several consequences to that. If that fails, if you fail to reply on that deadline, there are systems that we call hard real time. The idea is that missing a deadline is total system failure. I will have examples in the next slide. You have firm real time, which means that you can have some infrequent losses of deadline, but that will deteriorate the performance, and those replies, like those answers to your requests, will be useless, to be honest, after that time that deadline is reached. And you have soft real time, which is basically you can miss some or a lot of those packages, those replies at time, and you will only degrade the performance, but that won't be like critical. Just to make sure everybody understands here, a deadline in real-time workloads is like this. You receive this request, this event, you do the workload and have a result or response, and this response time cannot surpass a deadline, a maximum value of time that will depend on the workload. There are workloads that this is like a few milliseconds. There are workloads that means like nanoseconds or microseconds. So it will largely depend on the workload. Some few examples of hard real times. What don't you want to miss a reply on a system? Imagine that you have a pacemaker. You don't want that to fail on you. Imagine that you're having robot surgery on your heart. Missing a package or two may be fatal. Imagine that you have like this assembly line, and your sensor triggers something, that something is wrong at your assembly line, and you miss the time to actuate and remove that product or so. Maybe you have some catastrophic consequences, and you have to stop your assembly line, and that's terrible for like money. There are other examples of soft real time, which means that missing a deadline is not that bad. Imagine that you're having some online meeting, and well, if you can't just delay the replies for a long time, or else you are having this conversation and you speak something, and it takes for you like 3 or 4 seconds to the other part to listen. So that's one kind of a real time, which is really important. And well, Steam Deck, well, we were talking about Steam Deck earlier. Video games, imagine that you are like playing that game and you click your mouse and it takes like 3 seconds to do the shooting, and you lose the game, most probably. So that is some kind of thing that you have to have in mind, that you can't delay those kind of stuff because, well, it will degrade the perception and the quality of your service or product. Okay, if time is so sensitive, that means that you need to reply fast, and usually, historically at least, this kind of applications will run on top of bare metal systems, or meaning no operating system. And this is great because you can use the interruptions. You can use you can have some while loop running there, and it will get you very fast responses. But the thing is, and you, of course, you avoid the latency and like interruptions of the operating system. But well, programming some stuff like this may take a long time and may be very complex depending on your architecture. So, well, you can use an operating system. You have drivers, you have instructions, libraries. It's much easier to code on something that code your application on top of an operating system. So people created operating systems that are focused on real-time workloads like FreeRTOS, Zephyr, and RT-Linux. I will speak about some of them, some strategies they use. Because the whole idea is that you can't use a server-grade operating system to run these workloads, because those operating systems are focused on throughput. The amount of tasks that you run and not the time that you take to run them is more important, because, well, you have a lot of workloads. Processing them, taking a few more seconds, doesn't matter. You want to have a lot of output. And real time is not like that. You need to have latency. You have to deliver the task fast, even though you are like wasting resources on that. Well, Zephyr, for example, you have a simpler kernel, a lot of real-time oriented mechanisms like locks and queues. You have many schedulers available, and for different RT requirements. So you can opt for having more performance if your real-time behavior is not a hard real-time, for example. FreeRTOS, the whole OS is deterministic. You have a lot of allocation options. So also, you can like have better performance and depending on your real-time requirements. RT-Linux is something very interesting. The idea is that you have a thread for running Linux, and it's kind of virtualized because it uses a virtualized interrupt control. I have an image on that. But the idea is that you have these real-time threads that run from RT-Linux, and everything else that's not RT are run on a thread that is like a guest VM with Linux running. Something like that. You have RT-Linux. This is a thread. The RT workload will run as a POSIX thread here from RT-Linux, which is not Linux, is a completely different operating system. And one thread is Linux, which is the usual Linux that have all the features and tools that we are used to. And the no-RT tasks run here. When you have an interruption, and it's an interruption for Linux, it will go into interruption handlers of the RT-Linux, and then to this virtualized interrupt control, which will go to Linux and then to your tasks. But when you have an RT-related interruption, it will just go to interrupt handlers and RT workload. So this way, you can just like schedule out the whole Linux operating system and just focus on your RT workload. It's a very interesting concept, but here you have the limitations of a very restricted kernel. It's not like programming Linux, okay? It's like programming on a much more, in a system with much less resources, much less tools. You can't use everything that you are using on Linux. Well, on that, what about Linux? Is Linux an RT operating system? No, it's not. It was planned for real-time, not for real-time, but for performance. It focuses on throughput instead of latency. You want to have a lot of things done. It doesn't matter how much it will take. So it makes a lot of sense for server workloads and have no deterministic behavior, meaning that you can have a loop, or it can take much more time on given system call on some situation and be really fast in other situation. And the workloads can and will be interrupted by the kernel or by other tasks that for some reason need to run. So this will cause missing deadlines, which are bad. Remember, the whole idea here is that we don't want to miss deadlines because that's fatal. Well, but Linux is great. Everybody wants to program on Linux. It has a lot of tools, a lot of features. Much easier to work with that than working with like bare metal. So, well, you can use practically any computer language, programming language that you want to use. You have libraries, you have tools, you have GDB, you have GCC. You have an extensive hardware support. I believe most of you have seen the Linux kernel code, and it's a lot of drivers there. You have a lot of options to choose from if you are a hardware vendor. You can assemble your solution with many hardwares and use the drivers that are already there. And you have the source. So if it does not fit your needs for some reason, you can just change it and use that like that. So the whole idea is how can we improve Linux to be more like a real-time operating system. The first step, which is already, the whole part 2 here is about things that are already in place at Linux. So everything that you see in part 2, you can already use its own mainstream.
Just a question before we get into it. For how long have these been part of core Linux?
Some of them a long time, some of them are more recently being merged, like Preempt RT is being a long time, but was not upstream Linux. Now it is. So it will depend on the feature. There are a lot of features.
Yeah, just to give you an idea, I think I talked about that at LinkedIn in one of my posts about your presentation. I mean, when I was at university, like 20 plus years ago, I was working with a set of patches from Politecnico di Torino that enabled real-time on Linux kernels. It was probably a completely different design from what we have today. I don't know much details about today. At that time, it was like they have, the scheduler had a separate high priority queue that basically you used to write kernel modules, and this high priority queue was scheduling these kernel modules with higher priority than the user space tasks. So that's the solution they provided at that time. It was good because you had Linux, but at the same time you had to write kernel modules to run real time. Now, when I joined IBM back in 2006, IBM had a team dedicated to enable real time on Linux mainline. So this is not a new talk. I mean, this is something that has been happening for more than 20 years. The thing is that, Linux is much more prevalent today than it used to be. As Leonardo said, I mean, everybody wants to use Linux because it's just easy, right? So that's why I think this has grew in importance in the past years.
Yeah, that's correct. Well, let's retake that. Your question is, okay. The first thing here is scheduling. The scheduler needs to shift from a performance-oriented scheduler to from performance to a real-time oriented scheduler, and we have this. We have those are the ones that are usually used. They are performance-oriented, but they are also the sched FIFO, sched RR, sched deadline, which are real-time oriented. What is the idea of the real-time scheduler or real-time oriented schedulers? Is that they pick the task with the higher priority and don't let them go until they are finished, okay? That's the whole idea. It varies though, it's somehow different between them. Sched FIFO and sched RR are basically the same when you have a single task in the higher priority level. The idea is that they will run that until it's finished. And sched deadline will seek this, will calculate with parameters that you pass about your task to decide which is the one that the deadline will finish sooner. And it will pick that, and until the deadline is over, it will work with that, and then switch to another task. SCAD FIFO and SCAD RR, which is round robin, vary when you have multiple tasks on your higher priority level. So the idea is that SCAD FIFO will take the task and run it until it's over, and then switch to the next task. But the idea is that it will choose the task that was scheduled first. So that's why FIFO. If you schedule in time here, task A, then task B, then task C on the higher priority level, and you have on your lower priority level task D, task E, and task F, it doesn't matter the relation in time between those two. Since this is the higher priority level, it will do them first, in order in which they arrive at the processor. SCAD round robin will take this limited time slot and will use those time slots to run parts of those tasks, and it will run here a part of task A, then a part of task B, then C, and then go back to task A, B, and C until they are finished. And then when those tasks are finished, it will go to the lower priority tasks and do that there. The SCAD deadline here, it will calculate which deadline will be due sooner, and we'll work on that before. Here you have this deadline will be finished before this and before those, and you have them in order here.
So
sure.
Brás, in the previous slide, you said that the previous one, the SCAD deadline you have to provide some more information about the runtime and the deadline to the scheduler. So how do you calculate the runtime in this case? Because this can vary a lot depending on the architecture, the processor, and number of parameters. Yeah,
that's something that the person that is programming the real-time workload will be the possibility to provide if he wants to use this scheduler. It's kind of hard. Yeah. That's why we usually will use the SCAD FIFO, which is much easier and less interrupted. So.
Yeah.
Sure.
So going back on the same slide, this means that you can have a process sleeping with the lock.
Oh, sorry. This is after. Sorry. I will reach
No problem.
Sorry. I
was asking a question.
Oh, you went forward.
Yeah. Okay. I was asking a question about this one, but he go.
Yeah. Sorry. I didn't see. Sorry. I will reach there. Please go on.
What's the difference between these scheduling policies and the ones from FreeRTOS, for example?
No idea. I'm not an expert on RTOS. I just presented them as another option. But the idea is that Linux is much more complex, so it deals with more stuff. So that's the idea.
So we have a specialist on Zephyr.
Just tracing stuff.
Okay.
Going on. Preempt RT, what is it? The idea is that you have this option which was quite recently merged in the kernel, like a couple of years, which enables you to make Linux a fully preempted kernel. What is the idea? What is preemption? The idea is that you can you can interrupt the kernel, which usually is not very useful to happen because programming a kernel which is interruptible is kind of hard or inefficient. But you can enable this and have your kernel to be preempted or interrupted, right? By user space code, if nothing else. So what does change it? It will replace the lock primitives, spin locks, read-write locks, etc. And you can have a sleeping spin lock, for example. They are preemptible, have priority inheritance. And with that changes, those changes that were proposed by Thomas Gleichner, I suppose that's how it's called, you can make the kernel mostly preemptible and break those long tasks that were previously not preemptible. It comes with a cost, of course, but you get like more real-time behavior on that. It can be enabled or disabled depending on whatever you're doing. So don't worry, like, will this be something bad for my workload? If you don't enable this, it's fine. You don't need to. It's just for real-time workloads. Well, of course, some parts like the scheduler can't be like printable, so or else you have a mess. So there are some pieces of code that can't be printable. And for some reason, okay. Why is kernel preemption good for real-time workloads? If you have a workload which is higher priority, it can stop the kernel. And if you can stop the kernel to do your workload, you can get CPU time before. And then you can like run that before and give the answer before, the reply, the result before previously. And that means that your deadline is less possibly being missed.
And at the same time,
yes,
you can maybe create some kind of denial of service in the kernel.
Yes.
Is there any protection against that?
I'm not that expert on that part, but the idea is that you can still be interrupted by some stuff on the kernel, some housekeeping stuff. And that's not like you will run this full % of the time. That's why there are some other changes that will improve that. But even though just for the idea of this presentation, we are still hitting some issues with that. I'll reach that, and it's more on the end of the presentation. The idea here is this is something without preempt RT, this is something with preempt RT, and you have a key user code, you have here user code, you have the scheduler, and you schedule some kernel code here, and this kernel code is interrupted by the, let's say you have this real-time request, which is an RQ, so for example, a sensor, a GPIO sensor, it will cause an interrupt, the kernel will deal with that, go back to work with the whatever it was working on, and then it will schedule it to your user code again. With preempt RT, you can, like, after this happens, you can schedule out your kernel code and do the user code, have the reply here for your request, your real-time request, and then you go back to kernel code here. So mostly you have higher priority than the kernel, so whenever you need to do something, it will happen faster. That's the whole idea here. Next feature that's interesting for real time is the CPU isolation. Well, what is it? It's a kernel boot parameter that removes the CPU from the list of CPUs which your scheduler can automatically assign work. So when you pass a given CPU to that parameter, you say, well, Linux, don't schedule anything automatically on here. And then after that, you need to schedule your tasks there manually, pin that to your CPU so they can run there. There are further options on this, which you can like disable tick, which is a timer interruption to check if there are any other tasks with higher priority to run on your CPU, but the whole idea here is that please focus on the CPU isolation thing, that don't let the CPU, the scheduler to put any task on there. I have a image here so it's better to understand. What does it change? I've already gone through that. So you have less interruptions here because your CPU is not running like 5 tasks. It's just running 1 or 2 tasks that you manually assign it there. So there is a your real-time workload will have more CPU time and the processor fully available for it. So there are less interruptions, less scheduler interruptions, let's say. How does that improve the real-time behavior? You have the CPU all for yourself. There are less tasks running there, so you will, in the end of the day, have more CPU time, which means that you are less prone to miss a deadline. Here is a picture, so it's easier to understand. When you don't pass a ISO CPU parameter, in this example here, it has 4 CPUs. So scheduler knows that it can schedule work on 0, 1, 2, and 3. So here you have CPU 0 with a lot of tests, CPU 1, CPU 2, and CPU 3. And when you pin a task on CPU 3, it will like compete with for CPU time with the other tasks that can be moved here. When you pass your isolate CPUs for this example 1 and 3, CPUs 1 and 3 are free. Scheduler won't automatically schedule anything here. So you have to manually ping a task here, and this task will run without any competition. So you are sure that you don't have anything else running on that CPU. The other feature is no hertz full. The idea is that you disable the tick, which is this interruption, this timer interruption that checks for different tasks that can be a higher priority, which makes sense on situations where you have an isolated CPU, for example, that there is nothing else running there. You don't need your scheduler to be from time to time interrupting your workload to check if there is something else to run, because you guarantee that there is nothing else running there. You can only enable that if you have this configuration here in the kernel. So it also offloads the RCU callbacks, but I won't get into details with that. Well, disable the check. So your workload won't be periodically interrupted. So less interruption to your workload. And this is nice to the RT behavior of your operating system, because you won't have those ticks happening and interrupting your RT workload. So there are less chains that you will receive a request and your CPU will just have this tick and the scheduler will run, and then you'll miss your deadline. Something like that. The scheduler, let's say this is the tick, periodically, and after some time it will try and check if there is any other tasks here. And let's say that you get a real-time request here. It will only process that after your scheduler finishes verifying, so you can have a higher total time, like this can be greater than your deadline. And with no hertz full here, you can just process it because there are no scheduler interruptions. That's the main improvement, let's say. Well, then this is part 3. This is something that will require some knowledge with kernel, or at least with locking primitives. I'm not sure how many of you will be able to, but I suppose all of you will. The idea is that we have an issue, which is what we are talking about, inter-process interruptions. Let's say that we want to clean the cache, for example, for all the CPUs, and we have a routine that needs that. That will still happen. We will still have these IPIs that will interrupt the kernel. So it will interrupt your workload to happen. And those, will interrupt your RT workload, so all the problems that you may miss the deadline still happen here. We get a lot of those in the field, in production. So the whole idea here is to avoid those inter-process interruptions. The cache cleaning situation is not the usual situation, because that needs to happen this way. But there are a lot of IPIs that are not necessarily, they don't need to be an IPI, okay? Well, why this is a problem for real time? These IPIs will schedule out your real-time workload and take time, and we don't want that. So you have an inter-process interruption here. It will have a context switch. You run your IPI, and then you have another context switch. So let's suppose that you have your real-time request here. It will take this much time to process that. It could take just this much time if you don't have this IPI here. But of course, some of them are not non-negotiable. This is hard to solve. Like, we can't just remove all the APIs, as I was saying, because that will be very bad for the kernel. There are very efficient parallel programming algorithms that use API. Basically, they use local locks, and local locks are just for your local CPU. In many situations, it will just like disable preemption. For real time, you just get a spin lock, which is local, so it's very fast. And then you just use the API very not oftenly. So it's a high price to pay, but overall it's very efficient. But it's not good for real time because those APIs are bad for real time. So there are a lot of APIs around the kernel because of those highly efficient parallel programming methods. And each case of those APIs, each case we have to use to remove these APIs will require a lot of study. You can't just like remove all of them and have your maintainer to think that it's okay to do that. It will touch very important code like memory management code or C group code, which is stable for a long time, and we can't just like remove or change that in a batch. Okay. So there is no general API replacement solution. Every solution of them will take time and will take resources. And will take a lot of conversation with your maintainer because some of them are perceived as drastic changes. And you will find a resistance from the maintainers. And of course, it's their job. So the whole idea is, if it takes a long time and each case is really important and it requires a lot of work, how can we decide which API is the most important to remove first? For this, I propose the solution of a trace point, which you can enable, and whenever you miss a deadline on your code, you can get the logs from the tracing. And with that, you can see and you can check which APIs are bothering your real-time workload. And it's very specific because it will depend on the other things that are running on your processor. So you can use that. The idea is that they are called CSD function entry and function exit. So in our scenarios, we enable everything, no heartful, scad FIFO, and preempt RT. Isolate the CPU, and then you keep track of your deadline. You can like put a debug on your real-time workload, and whenever it misses a deadline, you get the log, and you compare it with your times and see what was running, which APIs were running during your time slot for your real-time request. So you will see something like that in the end. You have this real-time request, you have entry and exit of a few APIs, and you have your last time here for your deadline failing. And you can see, well, this is something that is bothering my my workload, but this one here is bothering it more. So I can try to deal with that first. That's the strategy that we are currently using to determine which API we can remove first. What else I'm working on? Well, removing these APIs. There are some low-hanging fruits there. There are some algorithms there that use all the processors to distribute some workload. For example, pcrypt. Encryption can be expensive. So pcrypt will give for each processor that is online on your machine, it will give it some work to do, part of the encryption work to do, and that's great. But if you have an isolated CPU, you probably don't want that. So in this case, the change is really simple. You just say to your algorithm, well, if it's an isolated CPU, don't schedule work there. And that's basically why I proposed it here. The idea is that you get this housekeeping CPU mask, which will say, well, these CPUs can do work queue stuff. And this CPU mask is basically a integer which have 1 bit for each of your CPUs, and we'll just have a 1 if the CPU is able to do like work queue stuff, and a 0 if it is not able to. So the patch here is simple. I just get this CPU mask and I do an AND operation, logical AND operation, with the online mask, and I only schedule stuff there. So basically what I'm saying to the algorithm is, it's isolated, don't do pcrypt work here. There are this, I saw this at least in 3 very important points in the operating system, in the base operating system, which they use local lock, schedule work on, and we can replace them with spin locks. But wait, spin locks are locks are expensive, right? So the whole idea of using local locks and schedule work on is to avoid having locks in your hot path, okay? So why am I trying to replace them with spin locks, which are, in this case, expensive? The whole idea is that if you can have a spin lock that is you only get this lock, or you mainly get this lock on your local CPU, like a per CPU spin lock, you don't pay a huge price. You pay like 12 clocks, for my experience, or down to even 5 clocks, if clock cycles in this case, for getting a spin lock. So it's not that expensive to replace a local lock with a spin lock. Of course, it's a cost. It's some few cycles. If you run that a lot of times, you will pay some price. But with that, you can remove this API. So it's useful for real-time workloads. How does that work? The idea of spin lock is to avoid parallel execution, like you sequentialize it, so you don't access memory with 2 processes at the same time. And the same strategy is valid for local locks, okay? When you schedule work on a remote CPU, you just say to that CPU, run this locally, and the local locks still work fine. So with spin locks here, you, instead of like interrupting your remote CPU to do something, and those some cases are just in software cache, for example, you can just like get this spin lock remotely and just do the work and don't interrupt that CPU. It's not that expensive. Schedule work on picks at least 1 global lock and a local lock. So it's much cheaper to do this part of schedule work on. The thing is that this is not run as oftenly as the local lock part. So there is some price to pay. My argument is that this price is not that big. So it's worth to do that if you are running a real-time workload. That's how it should be looking like. Just a minute. That's how it should be look like. You have, currently in the kernel, you have this local lock here. You do the local work and then local lock. And when you have a remote CPU, which you work to do some work on, you have to do some work on, you just schedule work on that CPU, and that's it. And what will this trigger? It will trigger an API, and the remote CPU will get this work queue and do the work there. This is what I'm proposing. You get a spin lock instead of a local lock, do the local work, and then spin a lock. This is the local work. And if you are doing a remote work, for example, you get that per CPU struct, and then spin, lock it, spin, do the work, and spin, unlock it. So it works great instead of a scheduled work. Okay, this can be done, and it's really interesting that, to be honest, I found out that real-time, the preempt-RT kernel already uses spin locks instead of local locks because it can't disable preemption at will. So it's a low-hanging fruit. You already get a spin lock every time in preempt-RT kernels. So there should be no issue if you just get the spin lock. I mean, you're already getting the spin lock on the hot path, which is the higher price to pay. So there is no issue if you just get the remote spin lock and do that. And today, as we are talking, the upstream kernel will get the spin lock, which is expensive, and then schedule work on, which is both much more expensive and will be bad for our real-time workload. So what I'm trying to do upstream today is to convince people to just get, it is already getting the CPU, the per CPU spin lock, so please go on.
Yeah, don't you create a scalability issue on the non-RT columns when you replace the local lock with the spin lock on the hot path?
Sorry, can you repeat the question?
So on non-RT columns,
yes,
right, when you replace the local lock
yes,
on the hot path,
yes,
with the spin lock, you create a scalability problem.
Scalability?
Yeah, scalability.
Well, it's a local spin lock. So that spin lock will only be at your local CPU, and it will only mostly be gotten in your local CPU. So the cache line is there. So it's a local cache line. You don't usually have this remote CPU touching your cache line. Okay?
So it's a per CPU.
It's a per CPU spin lock, of course. Because if it's a global spin lock, then it's all in the trash here. Okay? It's okay?
Yeah, that's good.
Okay. The idea here is that the preempt RT kernel already has a local spin lock, which it gets for doing instead of the local lock, and it's still doing scheduled work on, which is known to be bad for real-time kernels. So I'm proposing an interface in which, if you are using a real-time kernel, instead of doing scheduled work on, it will just grab the remote spin lock and that's it. In this case, if you schedule work on something, you're already touching the cache line. So it's a win-win situation. You're just not having to do a very hurtful work for your real-time workload. And that's it. It was faster than I expected, but do you guys have some questions?
I have a question. I mean, when we are doing virtualization, it's a little bit different. I mean, just something that I crossed my mind. I mean, when we are doing live migration, for instance, and if the live migration takes some time, the kernel complains a lot about being stalled, right? You have RCU stalls, you have block device stalls. You can have a bunch of error or warning messages saying that things are just not working. Does that happen with RT kernels? Because I mean, you are disabling the timer tick, you are disabling the RCU stuff, you are disabling the scheduler. I mean, doesn't the kernel complains about that?
That's the good thing about it. You are enabling all those stuff, but they are enabled per CPU. So let's say that you want to do a live migration or something like that. You can do that on the other CPUs that are not isolated. They don't have the check disabled.
Yeah, I mean, but I'm not even thinking about live migration. I mean, I'm thinking about the regular stuff that is running. Because I mean, even though you have a CPU that is isolated for the real-time tasks, there is still other stuff that the kernel probably wants to run there, right? So. Yes. Doesn't this other stuff complain about not being able to run?
That's the thing. Those things will be running there. You can't, at the current state, we can't just say that no API will be running on the isolated CPU with all those options. So that kind of stuff is the kind of stuff that we can't remove. All we can do about this is try to make it as fast as possible, so it won't bother the... So the whole idea is that we want the kernel to still working. I understand that if we just say, well, you won't be running any API here, the other CPUs will get stuck, and the kernel will complain. So there are stuff that we can avoid, just like this example where you are only touching software. So you can avoid these APIs, but there are APIs that can't be avoided. So all we can do is try to make it faster.
Okay, thank you.
Sure. Go on.
So I'm just, when you're talking about the CPU isolation, just came up to me. How do you handle thermals in real-time system? So like, imagine you're running the same task in a processor. It will heat up, and you might get a CPU throttle. And related question is, I remember reading that the kernel had some code to schedule tasks to average the thermal down, and I imagine for real-time systems this is not great. Right?
Yes, that's correct.
So how is there any smart way of handling that in real-time OSs?
Well, I can't say for every real time, but I know that when you are running a real-time workload, it's mostly a workload that will do some work and that will go idle. That's why we have to say that this task, well, don't schedule it out. It's idle, but we want it to be ready to respond for any request that comes. So the idea is that the other CPUs will run just fine. Linux has this balancing for thermal and stuff, but the isolated CPU, as it will mostly be idle and do some workload there and just stop for a while, I don't see, at least in field, any thermal problem there. And no throttling, because, well, it will throttle if you have a lot of workload in there, right? Does that make sense?
Yeah.
Okay.
So you just schedule small critical paths to the CPU.
Sorry?
So you just have to schedule small tasks.
Yeah, real-time workloads are not usually very time-consuming, but let's say that you have a lot of requests and it hits some. Then you have some deadlines missed probably because of the throttling, but that's part of the specification. You can't just a lot of requests. You have to project your system to respond for a limited amount of real-time requests, or else, well, we have limited CPU time. You can't, in any way, in any real-time OS, you can't just overload it with requests and expect it to fulfill the real-time requirements. Okay, that makes sense?
Yeah, and usually you have requirements on your system about what to do if you start to miss deadlines, right? I think your other question was, what does the system do, right, if you start to miss deadlines? I mean, I think that depends on what you are running and what your requirements are. So just to give you an example, when I was working with real-time kernels, as I said, no more than 20 years ago, that was because there is the CTI, the research center here in Campinas. They used to have a project with an airship, mini Zeppelin, that was autonomous, and we had an operating system that usually that was a robotic airship, so it has some vision, and basically it could fly alone, right, by itself. So one of the requirements that we had was that it should be a real-time system, because as it was driving the airship, there are deadlines about actions that you need to take, and if we missed one deadline at that time, there was a watchdog that basically rebooted the system, right? I mean, as it was an airship, I mean, it would not fall, right?
This is not running an airplane.
Well, yeah, I'll get there. So, as I said, I mean, an airship will not fall if you just have to reboot. However, there were like requirements, and I was the one building the operating system at that time, so I know this in quite detail. The requirement that I had at that time was that the reboot could not take more than 10 seconds to have the user space up and running with the real-time tasks, right? Because even though it would not fall, it would, for instance, diverge from its route, right? On an airplane, it's much stricter probably. First of all, they have more than one system running at the same time, and they compare the results, right? So if one of them starts to fail, they can just probably drop it and change to the other, right? They have some backups for this kind of stuff. So it depends on your requirements, and this will drive what you need to do.
Yeah, sorry, another question. So I think, maybe CPU boost is not a great thing for real-time systems, right? Like you increase the frequency momentarily for a CPU, and you get the CPU to run faster, but you also get it to heat up more. Yeah. And so do you just disable CPU
You can do that. You can use the CPU burst whenever you have a lot of requests, but usually it does not happen because it's well specified, and the idea is that you can disable it if you want. But well, maybe you have some burst and you want to use it. But the idea is that the workload is dimensioned, so your CPU won't get a lot of requirements. Requests.
You know, again, I think it depends on your requirements, right? I mean,
of course.
Just to give you another example from another area. So on cloud environments, usually you have Intel and AMD processors, and they have frequency throttling depending on the workloads that you're running. On cloud environments, this is not very interesting because the cloud provider does not want to provide you more CPU time than you paid for, right? And at the same time, I mean, you don't want the CPU to be slower than what you paid for as well, right? So varying performance in a cloud environment is usually not a good thing. And on the other side, I mean, cloud providers are not particularly interested in energy consumption at that level. Of course, they have the environmental concerns with the data center and using less energy, but not on that level. So if you get, for instance, Ampere, and I think Guilherme mentioned Ampere before. So Ampere is chip producer for ARM servers, right? And one of their pitches is that the Ampere processor that they are selling to Azure and to Google Cloud, it doesn't have variable frequency. It always runs at the same maximum frequency that the processor is capable because they want to have predictable performance on the cloud. So maybe for real-time systems, what you want is really predictable performance because predictability is more important than throughput in this case, right? So you probably want to disable frequency scaling, thermal control, all these things.
Yeah, that will majorly depend on the workload, right?
Exactly.
Yeah, the whole idea of like improving Linux is also for cloud. Clouds want to provide real-time able processors, so because they can get this share of the market, so it's interesting to have Linux doing that. And sure, go on.
So you mentioned that you cannot avoid APIs.
Right.
Right. So they are not maskable.
They are maskable, but when I say that you can't avoid APIs, is that there are some algorithms that deal mostly with hardware that you can't just avoid them. Let's say, get this example of like you have a TLB cache that you want for some reason to clean. You can't just like say, well, I won't do that because I don't wanna. The other CPU will be hanging, waiting for you to finish that, and the CPU, you'll send the response, and then after all the other CPUs like do this cleaning, it will proceed. So you get your CPU stuck. So you have to answer that. Even if we can, for example, speed up that or give some like deterministic time for that to happen on like a time at which the workload is sleeping for some reason, you can do that, you can improve that, but you can't avoid to do that on unlimited time or else your other CPU will get stuck. That's the thing that Leonardo Garcia was talking about also. That makes sense?
Makes sense, but I'm considering what do we do with NMIs?
NMIs, non-maskable interrupts. There are no maskable. You can avoid them. You can try to remove the source of them on the isolated CPUs, but you can't just like say that they won't happen. Sometimes they will happen, and that's a constraint. The idea is try to make them as fast as possible. That makes sense? Some other questions?
Thank you very much, Leonardo.
Thank you, guys. You want to use them?
Yes. We will be back at 4:30.
Okay.
Hello, everybody. Welcome to this talk. Title is Caring, Collaborative Testing in the Linux OpenCI ecosystem. So, who am I? I am a free software enthusiast for some time. I use it to contribute to the Linux kernel software. I also have some involvement in the Debian community and also several other contributions around. In the kernel, I use it to work, especially in the multimedia subsystem with cameras. And at the moment, I run a company called MonaDev and also work part-time for Collabora. And this work that I'm going to present is part of Collabora. So what is CI? So CI stands for continuous integration. It's about automation, test automation, and it's a bit more than just writing test suits. The advantage of it is, well, the obvious advantage of testing is quality assurance, but not just that, it's also about speed up development. I bet that you already had this situation where you write some code and it feels like you spent more time trying to test it, installing all the dependencies, figuring out how to properly execute it instead of coding itself. CI also helps you to cover different hardware and environments that sometimes you don't have. Already happened to me that I wrote some code, submitted, and received an email saying that I broke something in someone else's machine or hardware, but I didn't have the hardware, so I didn't know how to test it. So I was dependent on someone from the community to test it for me. And this takes time because we are all volunteers in the free software community. And so we need to coordinate, and this takes time. So if you can have everything automated, tested in several environments, you can be more certain that it works in several aspects. So it also speeds up the merge cycle. There are two types of testing, let's say. One that we call post-merge tests, which is basically when you run tests on top of the latest tree and report failures for future fixes. So usually you have a bot that runs, I don't know, in a certain period of time, let's say every day, midnight. And when it finds a failure, it sends an email reporting it. The problem with that is sometimes you have a bunch of things that were, a bunch of modifications that got merged in between those periods, and sometimes you don't have a mechanism to identify which was the patch, or you can have a mechanism, a bisection mechanism, to identify which was exactly the modification who introduced the regression, and send an email to the author of that regression. The problem with this approach is sometimes we end up with the works for me case, is when, well, okay, there's a regression, but I don't know if this is really important, because in a free software community, free software world, we don't actually know how many people are using the software, how many people are affected. We don't have metrics. We start having an idea when people start shouting on the internet, complaining, but it's not really clear. So people usually tend to, okay, it works for me. I didn't hear any complaints, or it's just one on another. I will leave it for later. And sometimes this judgment is correct. Sometimes it's a really corner case that it's not worth fixing. So you start getting an unreliable backlog that just fills up stress, and you start having several technical debts, and yeah, it's a bit non-manageable. And so we have pre-merge tests. So when the tests are run, when the patch is sent, and it only gets merged if all the tests passes, which fixes almost all those issues. and it prevents, in theory, introducing regressions if you have tests for it. CI can be quite complex because software can have several different setups, several different use cases, run on several distributions and systems, have several dependencies to be able to build, and different dependencies to run it. Dependencies must be updated also and maintained over time. Just a question so I can get to know you. Who here uses CI or work with CI? Nice, lots of people. And could you quickly mention which kind of tools you use? GitLab, Jenkins? Lava, GitLab? Jenkins? Nice. You do post or pre-merge tests or both? Both? Nice. So a few tools out there, you already mentioned. Well, there's a really huge list, but for those, I didn't want to bloat the presentation. So GitLab CI, for those who are not familiar with, we have this concept of a pipeline. So when you start CI, you can have a pipeline of tests. Those tasks here are called jobs. You can divide them by stages. You can have one job depending on the other one, not just for execution, for instance, if it fails in compilation, so we don't bother to execute the others, but you can also have dependencies on results. So you can have the result of one job used by the other jobs, and so on. This is very useful when you are building some jobs for building, or some jobs for building containers, and you can reuse those in other jobs. We also have, so basically a runner, which is a machine that is in GitLab, will pick up your test and execute it. And you can see this nice graph or UI in the website. The nice thing about GitLab, it is open source, so it's becoming very popular. Several projects are installing their own instance of GitLab. We have GitLab here in University of Campinas. We have GitLab for Debian community, for the graphics community, well, several others. The GitHub Actions, some people are using those as well. So it's similar, we have an event like a Git push, and there are runners and jobs and so on. And also Jenkins with a similar concept of jobs and pipelines. We also have board farms that are available. So here is a picture of a Collabos farm in Cambridge. And there are some software that helps you managing all those things. So basically a farm is a bunch of machines and computers, well, different devices, where when you trigger your test, there's a way to fire those tests to different machines, and you can see if anything breaks on different machines and different architectures. And there's this nice software called Lava, initially developed by Leonardo, which standardizes several things, the way it can manage the power cycle, so turning on, turning off those devices, how they boot, where they are going to get their rootfs, kernel, and the task they need to run. Also make available for you the output of the serial, the serial bus, network, and so on. Also provides you statistics, deals with the infrastructure. You can view results of the task in the Lava level, and so on. But there are also other custom bare metal labs out there where people do their own thing, but they somehow make it available to the community and integrated, and can be integrated by other projects. And in general, free software is bad at testing. So there is a lot of discussions in the community how to make this better. We have, for instance, in the kernel community, We have the kernel CI initiative under the Linux Foundation. We have several tools here and there, so K-unit test, K-self-test, and several test suites. So several subsystem have their own test suites and so on. But there's no standard way to do it. Everyone kind of do their own thing. There is no guideline or best practice, and this is what I would like us, and you were involved in this, to help me with this mission. And this can be a barrier for new contributors, for new companies to start getting involved with open source. Why? So one of the problems is upstream first can be very costly. Because when you deal with upstream, the works for me case, it's not enough. You need to care about usage from others. So when you submit patches, you need to wait for review. You need to make it work for others, which is a long discussion. And sometimes so that's why several people go there and just fork. Or do some closed source solution. Well, it's not why, but one of the reasons. And upstream first is good for the long run. So if you fork, have your patches there, at some point you need to update the base of the kernel, for instance, of the base of the software you are dealing with, and then you need to port all the changes to this new version. And if you make it upstream, it's there already, it's maintained. So if you don't do upstream first, you have a technical debt. But for small companies that doesn't know they will be for the long run, why to bother, right? So my point here is, if we make it easier, the development easier, with a high quality code that you can trust it, then we improve upstream engagement. At least this is my current thesis. But we have, so I think CI is a big tool for it, but then we have this other problem, is that maintaining a trustable CI is very costly. You have to maintain infrastructure, you have to deal with false positives, errors that the CI says it happens, but it's not the fault of the code that you send. You have to maintain it, update the dependencies from time to time, and you need to have fast reactions to fix issues, otherwise it will be broken and CI won't have any value. So if you don't trust a CI, so there is little value to it. The proposed solution here is an open CI that benefits everybody. One work benefits everybody, right? What do I mean here is, I would like us as a community, as an ecosystem, to have shared infrastructure, runners, machine network, shared hardware labs, with mechanisms to enable, disable it when they fail, shared tools for analytics, quality reports, error detectors, automated uprev, updating the dependencies for updating dependencies. All this available for the community, validated, maintained, trustable by several people. And what is nice is we already have this, and aside the Mesa 3D CI, and it's being extended also to the kernel first and the DRM subsystem. So what is Mesa 3D? So Mesa means Mesa 3D. So Mesa 3D is a 3D graphics library with support also for virtualization and translation. It supports most of the common GPU hardware, supports Vulkan, OpenGL, Direct3D9, OpenCL. If you use Linux, a Linux distribution, or even if you have Android phone, you are probably using Mesa. And the development is based on GitLab. So there is a server called freedesktop.org that is backed by the Xorg Foundation, which hosts those machines and this infrastructure. Here is one example of a Mesa 3D pipeline. And it is a small one, actually. There's another, because when you submit code, it doesn't execute everything. It depends what you change it. There are others that can be really big here. So test levels, there's a really nice talk this year by Dave Helderberg and Eric Nunes in DevConf, where they explain in more details all the tests. But basically, we have level 1 test, which is basically CI for linting and building and those sanity checks. Then we have testing on GitLab infrastructure, so x86, for instance, because runners are x86, and also virtualization, emulation, and software rendering. There's also testing on device under test, that we call it DUT, which sends the test to all those available independent labs out there and grab the results back. And if you want, there's also an explanation of this talk, explaining how would you do if you want to run your own lava farm. And maybe you could make it available to the community as well. So this is how the community workflows goes. So the developer prepares their code. They can fire the CI manually to see if it passes or not. Or when you think it's good to go, you submit, you open a merge request, reviews provide feedback, and this go back and forth, reviewing, resubmitting, and when the code is considered good, someone assigns the merge request to MargeBot. And MargeBot rebases the patch and triggers the CI. If CI passes, MargeBot merges the patch. Pun intended for MargeBot. But we have some bad days. So here's one example. So Marge replies, I couldn't merge this branch, CI failed, see this pipeline. And someone say, oh, it's not my fault, right? It's a CI fault. So reassigns to MargeBot. MargeBot tries again and fail, and it's not again. It tries again and fail. Then someone gets angry, and then eventually MargeBot merges your patch, right? And so when we have this kind of situation where we see MargeBot trying several times without code change in the middle. So here we see rebases, but the author didn't resubmit another version. We know that this is a bad case. And the problem is it's easy to track, kind of easy to track when things go bad, but it's not really easy to track when we made a real difference. So there was one person in the community who was really mad at the CI because it was blocking all her changes, and she wrote a really bad message there, screaming at everybody, and then I guess she regretted it, and she started this issue, which is called Mesa CI Appreciation Report, that every time she sees that the CI really caught something that really made sense. So there are cases there where, okay, this patch passed through several people, senior people, and no one caught this error, but the CI caught it, and she writes there, and this is really nice because, well, so we really know that someone is putting some value on it. So we have several farms. We have farms based on lava. I think Igalia has a farm. I'm not entirely sure at this moment. Collabor has a farm with around 250 devices, which are, so we have several, sometimes we have the same device of the same type. I guess there's around 70 different devices in the farm. We also have a farm from Valve, a farm from Google, a farm from Raspberry Pi that is available. There are several other tools which is available to the community. There's a nice tool called CI Uprev that will try to get the latest version of all the dependencies. So this is an automated tool that tries to update the dependency, run the test, and if test passes, it creates a patch automatically to the project, updating the dependencies. So it's very handy. And when it fails, it warns us, so we can go there and fix it. This is very nice because when we spend too long without updating something, the difference, the fixes is very cumulative and takes a lot of time to fix. We also have a tool called CI Collate that fetches a bunch of data from the pipeline, so you don't need to click on everything inside GitLab. You can quickly use this as a library to quickly script something and make it work for your case. We also have expectation files. So we have a list of what's expected to fail, what's expected to pass, and also a list of flakes, basically tests that we don't trust. And these two CI Uprev can also automatically update those expectation files as well. We have tools for detecting those the flakiness of those tests. We also have performance tracking, which is very interesting because sometimes you have a patch that made everything slower, but the test passes. How do you identify it? It's very difficult, so there are also tools to help with that. And there are several other scripts for a stress test as well. Here is one of the dashboards that we have. Here is basically, so there is more data that didn't fit in the print. I can send you the link if you're interested. This is all the open. And for instance, here we can see the number of merge requests is this line that we had in this day. And the blue line is the bad ones. Is the number of merge requests that there was at least one retry that shouldn't have happened. And we have here the percentage one over the other. So we basically can have an idea how mad the community is at CI, how pissed they are with that. We can have an idea if why testing are failing, because they are taking too long, or because this is the yellow bars, or because the testing are failing, or because infrastructure errors. And there are several other analyses. We even have tools that we can track in the unit test level and identify those unit tests that are flaking the most, and also analysis on the farms and on the devices as well, so we can identify if there's some device which with a bad network cable that makes everything close. And those tools, they are generic and very easy to adapt to other projects. We are including these inside Linux kernel DRM CI. So just for those who are not really familiar with the kernel, I think there are several students here. So the Linux kernel has a huge community, and so they divide in groups of working groups. So one group is responsible for multimedia, the other one is responsible for security, for network, for file system, and so on. And we also have this group called DRM, who is responsible for the graphics part of it. It stands for Direct Rendering Memory, if I recall correct. No, I don't know. I don't recall. Or direct, yeah, something like that. And the interesting thing is every subsystem that we call is like a separate community. Sometimes they even have their own code style for a few things. And they have also their own workflow. So we send, there's this patch, DRM, so initial CI subdirectory inside the kernel that adds support for CI using the infrastructure. And one interesting thing about GitLab is you can configure it with YAML files, and one project can include YAML files from other projects, so it's like an including library. And the DRM reuses the files from the Mesa CI to recreate their own test pipeline. Any developer can test their code using the infrastructure. And this is already available inside the DRM tree, right at the moment, not upstream, but at the moment under the topic, this branch, topic/DRM-CI, or Linux Next. We included the branch under Linux Next, so you can already test it. Here is the example of the pipeline. So in the kernel, so here we build containers. With all the dependencies for building, for executing. So we build the basically environment to execute all their other jobs. We have here, I know that it's small, so let me read it. Here the build stage, where we build the kernel for ARM32, x86, 64. We also build the test suite tool, that is IGT, in case of the DRM subsystem, but if it could be other test suite for other subsystem as well. So we build it here. We also build rootfs that will be used in the ARM machines mostly. And here are the tests in several different machines. So we have tests for AMD GPU, here for Intel, MediaTek, MSM, which is a FreeDrenal, a Rockchip, and here is the virtual test, virtual IO. So the idea is to expand this CI, and so DRM is one of the Linux kernel subsystem, and this model can be expanded to other subsystems and also other projects. So we could have this under multimedia, under security, BPF, network, file system, but also other user space tools, libcamera, I don't know which other user space tools there are, but one nice thing that we can have is linking one with the other. So GitLab has this nice feature called multi-project, that one pipeline can trigger another. So I could have a kernel, and for graphics, for instance, I made the basic test with the basic test suite, with its AGT, but I could also use this kernel it just built for Mesa 3D to see if Mesa 3D works well with this kernel. So this is a really full stack test. So the idea here is sharing as much as we can. If we have more people using the same CI base, the stronger it gets, right? The core of OpenCI is improved. So GitLab is basically the front end, let's say. We have other front ends, but we can have other back end as well. Kernel CI, for instance, or other tools depending on the project. But we sure have scripts for talking with the farms that can be reused by several others, and we could make this independent of the graphic subsystem and benefit everyone. we could share infrastructure tools and mechanisms, and if you have people using those things are improved. We could have more labs, increased test coverage, better tools, less false positives, and more reliability. And I'd like you to get involved, to contribute with it. We could have, I don't know if there are people from NXP here. I know that NXP has a farm, a lava farm, it could be included. RISC-V could have a farm, we could start testing on RISC-V. And if your company has like tools or like devices or could contribute to those testing, it would be really great, and we could share this work and everyone's benefits from it. That's it from me. Any questions? Any comment?
I have a question on the infrastructure side. I mean, just for me to understand correctly, I mean, in that slide that you show the presentation that on DevConf, right? So if I remember correctly, level 2 or something like that was the testing the x86 machines that you mentioned. So is these machines, this GitLab infrastructure, is this running at freedesktop.org?
Yes.
Okay. And then each company can provide access to their own farm.
Yes.
And integrate that to this basic infrastructure.
Yes.
So how does how freedesktop.org gets hardware for their infrastructure? I mean, who is donating that? Because usually, I mean, when we are talking about open CIs that other companies can use, my experience is that it's quite difficult to get hardware. I mean, everybody likes the idea of having a common CI and can see the advantages, but when you ask them for real hardware for the infrastructure, everybody, change the topic, right? So how do you get hardware for this basic infrastructure? Because I understand that the farms, I mean, if the company is interested, it will build the farm and integrate with this infrastructure, right? But you have to have this basic infrastructure that freedesktop.org has to maintain.
Sorry, but isn't the idea that you have your own hardware, physical hardware, and then you attach your infrastructure
that's
to
the
that
device under test, right?
Yes.
That's the level 3. But you need to have the basic infrastructure to coordinate the stuff, right?
So that would be my question, so you can probably answer.
Okay. Yes, there is this infrastructure, but the bottleneck's not there. The bottleneck are in the labs. We start getting several requests for testing, and the queue for the tests under the DUT takes more time, so there's a bottleneck. For the devices, this base infrastructure, I saw the name of the company who is providing that, but I don't recall at the moment. I can check later.
No, it's
but
just
I think it's a third. I think they buy it.
Okay. Yeah, because I mean, even though I agree that the majority of the test running time will be on the DUTs, you are running basic and virtualization tests on this basic infrastructure. So isn't that big? Because I mean, you have a multidimensional matrix there, right? Supporting a number of operating systems. So these things can get quite big, I think.
It's not big at the moment. We do, at the moment, the tests are mostly based on Debian. We do have a few, there are few tests on Windows, on Fedora, but it's just the basic things. So at the moment, the load is not big, but yeah, it could get big.
And then, of course, I mean, each hardware vendor or each company that is interested can get your own farm and integrate with that, right? So how does that work? Because, I mean, once you integrate your farm into this test infrastructure, is your hardware dedicated to this test infrastructure, or can you decide what to do with the hardware?
For instance, the Collabora farm, it is used for Mesa CI 3D, but also for kernel CI. There is a priority. We can set a priority there, but it's open, so the community will review it. You can If things start going bad, people can just disable it. It's just a matter of a commit disabling things. And
okay, so you have control basically, right?
Yeah.
Okay, first I would like to thank for all the good work on the DRM CI. I mean, it's great to have this in DRM. I'm one of the maintainers of the KMS, and I would like to know if you could integrate the KMS into this pipeline, because the KMS, I mean, we could run it in anything, like in the x86 machine, and the KMS is great to test like the DRM core, because we are really based on the DRM core and functions itself, and I mean, we have like a great support from IGT test. We have like a IGT test list in the IGT project, so is there a possibility to integrate the KMS?
One of the person who replied to the patch sent.
It was me.
It was you. Okay. Nice to meet you then. It is possible. It's just a matter of someone go and write the test, and it's there's nothing who would prohibit you to do that. And yeah, if you have time, please send us patch. We'll review and merge it. Yeah.
So I guess one question is related to the other question before from Leo, which is I'm a reviewer for a project called Apache TVM, which is basically a compiler for AI models. And the problem is that we've got a bunch of backends, and one of the backends is meant for embedded devices and for Cortex-M and that kind of small devices, and as once mentioned here, they are very fragmented support for them. So they have specific JTAG adapters, for instance. And the problem when I reveal the patches for the project is that quite often I need to run by hand the patches in each board. On my desk. So you touched on this subject, but I would like to hear more from you about the suggestions. For instance, what I would need to do, like I have, so Nordic folks have like 5 different boards on their desk, and I have my boards from, I don't know, ST. And I was hoping that there is a solution where I can, have those boards and run run some kind of software which could allows me to connect to your infrastructure. In that case, the Apache TVM project is using GitHub for CI, and I know that Jenkins, for instance, has that notion of master and slave combination where you can attach in your own infrastructure other slaves to the master. But I was wondering, what is your suggestion in my case? I'm reviewing, so they are using GitHub for the CI. I have those boards on my desk. So do you have any suggestion on how I could, automate, on how I can include those boards to be part, like a peer-to-peer thing, like even if the boards could disappear, I could turn off my computer, but other people will have the same board and we will attach to the CI. Is there any kind of solution in that sense? I was wondering.
So, right. So the question is, so you have some CI and GitHub, but they are not integrated with the boards.
Right, and there are many different boards which are available from time to time, or yeah, that's my question. What I would need to connect to use my boards. It's not I don't have a lab. I just have the boards on my desk. Is it possible to connect even for a couple of days that in ad hoc way, not in ad hoc, but in just for a certain amount of time, those boards as like a peer-to-peer protocol, and distribute like. Maybe it will disappear, but other folks will connect with the same boards or different boards, and it will enable the pipeline to go through that infrastructure to dispatch maybe tests, to those available boards. So, is there any solution I can use? Like if I'm reviewing, I will turn on that small infrastructure, it will connect to the CI for a couple of days, and I can run my review, and the patch can go through. But I will, because I'm asking for a kind of distributed CI, like from the community. Is there any kind of solution that allows me to?
So the idea is, if those types of devices are online, just send tests to them. If they are not online, so
right, it will appear
anything.
like they are not available, something like
Yes.
that. Because is there any solution for this? Is it possible? Do you see because people don't have those boards? I have some other people have other boards, and it's hard to have a whole rack with all those boards at the same time. So I was looking for a more dynamic way to attach that small infrastructure to just when I'm reviewing the patches,
I know. So, for instance, the Lava lab. So the hack there is just a matter of to easy connect everything. But in matters of big hardware, big infrastructure, I know that you don't need them. So Erico in that same talk explained a bit how you can build your own Lava lab with a few boards at your home. I'm not entirely sure if these mechanism of knowing which one is online and which one are not is available. I know there are a few other software besides Lava that it's limited in a few ways, but it's easier, I think, to set up at your house. But I don't think there is this feature of knowing dynamically.
In the main GitHub CI, I want everybody to look at the results just as my machine will be just as if my hardware would be in the same infrastructure, but it's a distributed thing, like that was something I was willing to have, which will help a lot to review, because there are so many. It's hard for a single company to have all the boards from Nordic, for NXP, from
in a single place.
So maybe the reviewers which are interested in that kind of hardware could provide, especially when they are reviewing the patches, which then we get that through the physical boards. Then we review and get the patch merged, and that will disappear. But it will work. I think.
Sure. Yeah.
So if you provide if you integrate your farm into this infrastructure, does the infrastructure control which tests run in your farm, or do you control which tests run?
So there's a mechanism with tags. You can put tags in the jobs, and the job will know which is the farm and devices that it needs to submit the job. So you can include your CI, say, I reply to this tag.
Okay.
So this is the same type of device of those others, or you can create another tag and say, just this job, I will execute for just those jobs.
Okay. Any other questions to Helen? Thank you very much. So we have 10 minutes before the next session, so you can have a little break.
about networking. I guess I got the wrong idea because this is a talk about network displays. Okay, anyway, it's done, so get on with it. So this is actually about screencasting, which is when it looks like this, which is when, oh, by the way, my name is Pedro Azevedo. I'm nervous, all right? This is me, and so this is a talk about screencasting, which is when you show the contents of your screen in another screen through the network, like magic. It looks like this in other operating systems, like Android, macOS, and the unholy one. Actually, this one's the unholy one. So you press a button, and like magic, your screen goes to another screen without wires. And this exists on Linux. It's done through this app called GNOME Network Displays. I know it doesn't look like much, but it's a lot. Trust me, you're going to learn a lot in this talk, and you're going to see that this thing here doesn't look intimidating, but it's a monster. And you're going to know why in a few minutes. So we need to talk, before we talk about network, we need to talk about the word before network, which is GNOME. I'm not talking about the mythological creature here. I'm talking about this thing that I'm sure you've seen it somewhere if you study here. This is the desktop environment that we have in our computers there in the lab. But if you're on Debian stable, it probably looks like this or something like that. Just kidding, no hard feelings, I love Debian. But anyways, so you have something that looks like this, and even this is not the entirety of GNOME, because this is just the desktop environment, and GNOME as a whole is a much bigger initiative than that. If we zoom out, you see what I did there? We zoom out, and you see the whole picture. And the whole picture is that the GNOME is a huge project that they develop libraries, and with these libraries they develop the desktop environment that I mentioned. Oh, I have to press the button. The desktop environment that I mentioned in the other slide, and also a lot of applications like this one. This is GNOME Network Displays that is going to be the subject of this talk. And also, okay, so this is GNOME. The whole picture, it's something like that. And so the real title of this talk shouldn't be the magic behind screencasting on Linux. It should be the magic behind screencasting on GNOME, because GNOME Network Displays only uses the GNOME technologies. Like it uses GTK, which is this thing here, for its graphical user interface. It uses libadwaita, which is also a graphical user interface library for its interface. It also uses gobject, which is a library for object-oriented programming in C, like vanilla C, not C++, the real C, but object-oriented C. It's a nightmare. It's very strange. You have to like pointers to classes, and then when you want to install I'm going to show you a snippet of code. It's very weird, and you're going to see it. It's weird. And so, okay, we're back to the magic behind screencasting on GNOME. And since we're talking about user space and kernel, I would like to interject for a moment. And what you're referring to as Linux is, in fact, the GNOME/Linux. I've recently taken to calling it GNOME plus Linux. Again, enough of this joke. I'm not sure. This is kind of an inside joke, but anyway. Have you seen this online, this copy pasta? Anyone? Okay, nice. Okay, so now that the GNOME part is out of the way, let's get to the second word of GNOME Network Displays, which is network. Network protocols, it's something that I'm going to explain to you. It's something I'm sure you're familiar with, which is email. Email is a protocol. It's actually a lot of protocols, but that doesn't matter right now. You can think of email as a protocol, and a protocol is like an agreement of how things should talk to each other. This is very important in networks because networks are just a lot of computers talking to each other all the time, and they have to agree on how they communicate. So email is a protocol. If you want to make an email service, you have to have a server for the server-side implementation of the email protocol, and you have to have a client for the client-side implementation of the email protocol. So the server implementation is going to be provided by whichever email service provider you have. It can be Google if it's Gmail, or Microsoft if your email is Outlook for some reason. And then for the client-side implementation, if you use a web client, you're going to use, well, again, Gmail or Outlook. If you have a desktop client, probably Thunderbird. They have a new logo. I don't know if you've seen this, but it's pretty good. screencasting is the same. It has a protocol. The most common protocol is Miracast, which is the one I'm going to explain to you in a few minutes. And you also need a server-side implementation and a client-side implementation. You need an implementation for the receiver that's going to receive the video, and an implementation for the sender. They actually have different names. The device that receives the video is called sync, and the device that sends the video is called source. I think it sort of makes sense because the device that sends the video is the source of the video, and then the device that receives it sort of syncs in the video. It's kind of a weird metaphor, I admit, but that's the way they're called. So the syncs can be smart TV. If your TV is not born smart, like mine wasn't, you can buy a dongle like this one to make it compatible with Miracast or any other screencasting protocol. Some projectors, this one probably is connected to the network. They can receive screencasting too, so you can project things without having to deal with all the wires that we're dealing here there. And so there are other protocols, like I mentioned, Miracast is one of them. The other ones are Google Cast, which is the one you have in Chromecast, and AirPlay, which you have on macOS and iOS. Miracast is the only one that's open source. That's why this talk is going to be about Miracast, because it's the only one that has an easily accessible spec file. Like I said, protocols are not code. They're just an agreement. So an open source protocol just has this agreement downloadable and freely available somewhere so you can know how communication is made between the things that implement these protocols. But Google Cast is proprietary, and AirPlay is also proprietary, so you can't know how things communicate when they're using AirPlay. However, someone reverse engineered Google Cast, and Google Cast is available in GNOME Network displays today. If you have a Chromecast at home and you want to try to mirror your computer screen to that Chromecast, it should work. It was done last year by a Google Summer of Code student who is my mentor this year. I'm going to talk about this later too. So the Miracast protocol also is divided in like 2 ways of working. It can work with Wi-Fi Direct, which is the most common way and is the way that I'm going to talk about. And the other one is MICE. I always forget what the acronym means. It's Miracast over Infrastructure Connection Establishment. It just means that if you have 2 devices that are not connected to the Wi-Fi, but they are connected in the same network, maybe through an Ethernet cable, you can make MICE work, but you can't make Wi-Fi Direct work. Wi-Fi Direct is wireless only, but MICE can work with wired connections. But I'm not going to talk about MICE today. Only Wi-Fi Direct Miracast. Okay, so enough of the weird words. So the Miracast protocol is divided in 3 easy steps, which are discovery, connection, and streaming. I think discovery is the most interesting and hardest part because there's an interesting problem that comes up. It's possible that one device advertises more than one connection. For example, if you have one device that's compatible with more than one version of Miracast, it may advertise both connections. And if you have 2 Wi-Fi cards, that's a copy-pasting problem. If you have 2 Wi-Fi cards, both of them will detect the same device, and then both of them will discover the 2 connections that are sort of duplicated. So these are the 2 ways you can end up with duplicated connections and duplicated listings of connections. And this is not good to show to a user in an application like, oh, do you want Miracast revision 1 peer-to-peer or Miracast revision 2 peer-to-peer? It's your choice. That's kind of weird. We only want to show the device so the user knows exactly what they're doing. Like, do you want to connect to this mirror screen device? And then ideally we should hide the complexities that this device offers more than one implementation of Miracast, for example. So the solution to this that's implemented in GNOME Network displays is MetaSyncs, not to be confused with any weird company. It's not that. MetaSyncs are just syncs that group other syncs. So I think I'm going to show the code. It's going to be easier if I show the code. This is object-oriented C, by the way. Very something. So the MetaSyncs have a list of syncs that it sort of guesses to be of the same device. And then it also chooses among these sinks the best one to be sort of the representative of that device. So maybe if we're in a scenario like this, it should probably choose this one to be the representative of this device because it has the latest version of Miracast. So we should probably only present to the user this thing here under the name of this device. So this is what we do, and then we can forward we can just pretend that that meta sync is a normal sync, and then we forward all method calls of a normal sync to the meta sync, which will be clearer with the code. So for example, if we have a meta sync, and we want to start the stream on that meta sync, we just say start the stream on whichever sync is the current sync. This was a lot, and it's over now. We're done with discovery. You can take a deep breath now. Nice, good. So we're gonna move on to connection now. Connection is easier and more pleasant and less full of syncs and meta syncs and similar names. So you have a source, which is gonna be your laptop or your computer or something like that, and a sink, which is gonna be hopefully connected to a display. And this is what I was showing before as the Wi-Fi card, which is going to be inside your computer, and the dongle for Wi-Fi displays. So we can forget about them right now and just think that you're running GNOME network displays on your computer. The first thing that happens after discovering the device and using the function start stream is that a Wi-Fi direct group is established between them, and then the source is going to ask, can you please give me a TCP connection? And when that happens, some devices are gonna ask like, GNOME Network Displays is trying to connect to this TV. Do you wanna allow GNOME Network Displays to connect? And then you're gonna hopefully click yes. And some devices don't do that. They sort of click yes for you, so you don't have to click yes. But after you confirm, or the device automatically confirms for you, it's gonna say, sure, and establish the TCP connection. And that's already the end of the connection part. Something that I should mention is, maybe this is somewhat familiar to you because this is how WPS works. When some routers have I don't know if you have this in your home, probably. There's a WPS button in your router somewhere that you can, in your phone, for example, say, okay, I want to connect via WPS. And then your phone's gonna tell your router, hey, can we please connect? And then your router is going to be like, yes, but let's wait for someone to press the button. Then they're going to be like waiting in silence, awkwardness. And then when someone presses the button, the TCP connection between them is going to be established, and you're done. So this is WPS2. It's the same mechanism. So connection's done, and the last part is sending the video over to the network display. This part is probably the most interesting because the Linux desktop is like a very diverse thing. Some people say it's fragmented, but I think it's kind of sad that you say fragmented. It looks like it's a bad thing. I prefer to say it's diverse. We're embracing diversity. So there are a lot of ways to do the same thing. A lot of different ways to do the same thing. For example, many people implemented screen recording in different ways. And for example, you have the KDE implementation of screen recording, you have the GNOME implementation of screen recording, you have the XFCE implementation of screen recording, and so on. And to solve this problem, there is something called portals, which is like the trendiest name for an API that I have ever seen. An API is just a way to... So the portals are like an API to the Linux desktop, because since there are many implementations of the same thing, a portal is like a front end, like an abstraction layer to the Linux desktop. So there is a portal for screencasting, and so every implementation of, of screen recording, so there is the GNOME implementation of screen recording that's done over on the window manager side, This thing here is the logo of the GNOME window manager. There's also the KDE implementation for screen recording. And this is Hyperland, which is like a bare minimum window manager. It also has its own implementation of screen recording. And then everyone can talk to the portal, and the portal will offer a very convenient way for GNOME network displays to understand all these things here without having to bother with all the implementation details and how these things here do things differently. So they all look the same in the eyes of GNOME network displays because screen recording is given on a silver platter via the portal. So this is streaming done. That should be the end of the talk. Just kidding, no. Actually, we are almost there because although we managed to discover the displays in the network and connect to that display and even send the video there, we are still using an app. So this is not one button magic yet. Remember, the other operating systems, including this one, they have just one button away in a menu somewhere. And we have to go through the trouble of opening an app. And this is not good. Of course, we envy this level of integration with the desktop. So this year, a few months ago, I got into the Google Summer of Code internship program, which does not mean I work at Google for the last time ever. It's not an internship at Google. I do not know anyone at Google, but Google just sponsors an internship at an open source project. I never spoke with anyone from Google, but they are giving me money to work on GNOME. So the internship is at GNOME via the Google Summer of Code project. That's it. Yes, not an internship. Please don't try to go to the Google Summer of Code if you want an internship at Google. It's not at Google, but anyway, if you want to be paid for an internship of a very short period of time in an open source project, Google Summer of Code is great, and it's a great opportunity. And my proposal and my mission for the Google Summer of Code project was to get the one button magic working for screencasting. So have something like this working on GNOME. And so these are my mentors. This is Felipe Borges, by the way. He's Brazilian. He was living here like a while ago. Maybe he came to Unicamp at a certain point. Maybe some of you know him. But he's one of my mentors. He's the maintainer of GNOME Settings, which is the settings application for GNOME. This is Jonas. He is one of the masterminds behind the window management and graphics stuff in GNOME. Exceedingly smart person, actually sometimes scary. The brain of this person needs to be studied. He's very, very clever. This guy here with a kite for his portrait is Anupam Kumar, which is the guy who reverse engineered the Google Cast protocol last year and implemented it into GNOME network displays. He's one of my mentors now. This is Claudio. He has been helping me with the community stuff, like user surveys and getting to know the other users of GNOME and testing if things are working out for everyone. And this is Alan Day. He's the designer. He's been helping me with, well, design. And okay, so how will it work? The main idea is to split these three things that were being done by a single monolithic app into three different things. We're gonna get there. One thing is the discovery mechanism. It's wearing binoculars, so it discovers the network displays in the network. And the other part is it's gonna handle connection and streaming. Since it's a streamer, it's wearing streamer headphones. So we have these two parts of GNOME network displays. They're now split. This part is done. Thank God. That took a lot of work. And between them is a manager wearing a tie. The manager is the one who's responsible to coordinate the messages between the discovery mechanism and the connection and streaming mechanism. And this is all done through dbus, which is a way for different processes in your computer to talk to each other. It's, I don't know if you've seen something like a REST API. REST API is an API that talks to the internet, like to every other computer in the world. dbus is like a REST API, but it only talks like in your local host, like in your computer. So everyone talks to divas. These are their birth names. So if you want to take a look at the source code later, you're gonna have this opportunity very soon. And so demo time. Where is this computer? Here? Is it here? Oh, it's like extended.
No, yeah, it's not.
Okay, no, I can see the cursor. This is important. Okay, so as you can see, demo here has a lot of quote marks. That's because it's not a real demo. It's just a mock-up. I have shown this demo in another conference, which is the GNOME Users and Developers Conference Everywhere. I was there like a month ago. It happened in Latvia, in Riga. It was very interesting to be there for this. And I showed them this, and they thought it was real. And they're now saying like, where is this? Isn't it ready? Because you showed it in the conference. It's not ready. It's a demo. It's a mock-up. It doesn't exist yet. So, yeah.
It's not going to work. It's the PDF. You didn't send
Oh,
the
yeah.
link to the Google.
No, but you're gonna see. It's gonna work. So, see? So this is your GNOME 40. This is your GNOME 46. Right now, the computers there in the lab are running GNOME 44. That's the latest GNOME version. There's gonna be a GNOME 45 out in like a few weeks. It's not gonna be there. Doesn't exist. This is gonna happen in GNOME 46. So like 6 months from now. So you can see the cursor, all right. So if you click this thing here, a menu appears. Oh, yeah. Oops, sorry. Yeah, a menu appears. And then right here, you should find a network displays button, like a quick action button. And when you click this thing here, you should find all the displays in your network. For example, this thing here is that projector there.
No, it's not. It's not Samsung.
And so,
It's this TV.
No, yeah, it's that projector. You can trust me. Yeah, this TV is also there. And so, if you click this, it's gonna take a while and spin a little and load for a while. And when it's done, you should find in the top bar an indicator that when you click the X, it stops the screencasting. It stopped. As you can see, it's not screencasting anymore. So this is the magic that I mentioned in the title of this talk. This is the illusion. And so future work, to begin with, is what I just showed you. That's future work, as it is not ready. But this is almost ready now, for real. It should be ready. The deadline is in September 11th, which is very near. The end is nigh. So let me take this again. But anyway, in spite of this, I also wanted to implement some sort of way to rename devices because, you know, as you saw in the demo, it's very hard to tell which device is which. I mean, we just mixed up the projector and the TV because their names are not very intuitive, and that happens all the time. Their names are like Samsung 36-inch, Verizon 4, 39. It's terrible. So it would be nice if we had a way to rename devices, for example, living room or office, projector in office, IC34 or something like that, so we know exactly what we are connecting to. This is also nice for you, for example, if you are here in a place that's full of projectors and full of other rooms, you don't want to accidentally cast your screen to another room and be like here waiting for the things to appear and it's actually casting somewhere else. Or like start casting the TV in your parents' room. You don't want that to happen. So it's better if we have a way to rename things. The other thing that I wanted to implement, and that's going to be probably a little harder, also has to do with making sure the user is looking at the display that they're casting and is presenting a way for them to confirm and make sure that they're actually looking at the thing. So maybe show some icons in their computer and ask, are you seeing the same icons in the TV that you told me you were trying to cast to? And then if the user says yes, then it starts sharing their screen. There are different ways of doing this. We thought of perhaps having like a pin, like showing a number here and asking the user, what's the number of the TV, bro? And if they don't put the number in the TV, we're gonna say, it's in your parents' room, man. You can do this. But this one's more friendly. No one wants to type pins. This would also probably only happen like in the first time you connect to a display, just to make sure you know which hardware you're talking about. And that's all, actually. That's all. You can scan this thing here if you want to see my other social media. My website is here. I don't have Twitter because Twitter doesn't exist, but I also don't have X. And yeah, that's all.
Any questions for Pedro?
Please do not no questions about the network stuff. I did not do that. I only learned that. You can ask me everything you want about the dbus part, the splitting the things into modules, but the network stuff, man, is it complicated. Oh my God. But you can try, you can try. We can try to answer, to come up with a way.
Very specific question. Is there maybe a chance you can stream touch signals? Like if you have a touch display, then you can maybe? Like
Next question?
Okay.
No, yeah, probably. This would probably have to be implemented somewhere in Mutter, which is the window manager. Because the window manager, it has this terrible name of window manager, but it also takes care of a lot more than managing windows. The window manager is also responsible for dealing with input a lot, like your keyboard and your touch input. Because, for example, now we have a new protocol for window managers, and for some reason, touch gestures work much better now, which is unexpected because when you have a new protocol for window managers, you think the window management's going to improve, but for some reason the input also improves a lot. So to answer your question, showing touch touch events could probably happen in GNOME network displays as long as support for this was implemented in Mutter somehow. That's how I think it could happen. Yeah, that's.
Question about the part. Is that going to be exported as a monitor, like a display that users can use to extend, and so it's like a virtual display there? Is that it?
Just such a great question. If I don't know one question that I know the answer, exactly I know the answer. Okay, so the GNOME Network Displays app has the capability to create a virtual monitor, and then you can use that virtual monitor to extend your screen as if it was. You can treat the display as an external monitor, but this is not what's happening. That's not what's happening when you mirror your screen. When you mirror your screen, you're gonna take a video, make a video stream of your screen. You turn that into a GStreamer object, GStreamer elements, or something like that, and you just send that to the display. But the window manager, Mutter, is not doing anything at all. It's just recording the screen. It's not aware of the monitor. One thing that we discussed before landing on this design was having. Actually, the first idea for the internship was to integrate the functionality of GNOME network displays in GNOME settings as part of the display, like the monitors settings, and just have them appear as if they were monitors. But we decided against this because, as you can see here, it's very weird. Where's the cursor? Where's the cursor? Oh my God! Look. Okay, yeah. See, it's very weird when you have a 3D space to map things on a 2D plane. Because when you have multiple monitors, you have to arrange them in a 2D, because they have to be side by side somehow. And when this sort of setup happens, I never know, is the computer, make your bets. Is the computer gonna be down, up, left, or right? Left. Anyone else? Any other bets?
It's down.
Down. Yeah, see?
Because I configured it down.
Let's see. And yeah. Yes,
but
it's
the
down.
default is left. Or
See?
right, actually. I think.
So we decided against the idea of having virtual monitors, just because it could be confusing for users to be in the screencasting, usually people are sitting or on the side, or you usually don't have your screencasting monitor and your real monitor side by side. So it's confusing to have them mapped in a 2D plane when it's clearly not 2D.
Arguments. We can configure like Leonardo Garcia did. You can configure it depending on what you are doing. So let's suppose you are with your laptop at your left and you have to screencast at the television. It would be great to have this as a virtual monitor, even though the usual case scenario would be like having this mirroring, but also displays can mirror stuff.
Yeah,
that would be great.
I agree with you because for instance, I mean, my TV does not support Miracast or whatever, so I never tried GNOME there. So I usually, when I want to watch something in the notebook and cast to the TV, I just put an HDMI cable, right? And I set up everything. It's just an extended monitor. I push everything I want to the TV and close the laptop, right? Yeah. And then I watch. So for me, it's a screen. I'm not going to use the laptop anymore until the movie finishes or whatever. Now, if I'm working, and I have worked before with big screens and TVs, and it's great sometimes. I am also using an HDMI cable in the same way, and even though things are not in a plane, it's just a question of configuring, and you can set up the best way that you find out. So, yeah, I mean, that's probably just an opinion, but I agree with you. I mean, I don't see a problem, and I think it would be even easier because it's the same kind of interface, at least, right? That you are already used to. I mean, yeah. But anyway,
I can talk about the long-term future problem, the long-term future plans, which are, first, the app is going to stick around. And the app has the capability for a virtual monitor. The idea is just to have the most common workflow integrated in the desktop environment. Just because, if your grandma uses GNOME, we want her to feel at home and not be like, where's the cursor? Where's the cursor? Is the monitor left, right, or anything? So, but the app, there's probably going to be a lot of work in the app too, because as you can see, it looks ugly as hell. But like if you look at this, oh wait, other way around. We're gonna get there. Trust me. Yeah, that's a lot of slides. It took a lot of work. Yes. And we're here. Okay, as you can see, this app is an aberration. It looks actually terrible. But if we're gonna do some work to make it look better and behave better, what happens when you enter the app, it doesn't even ask if you wanna extend or mirror the display. It offers you to cast to a virtual monitor. And you have to know that if you cast to a virtual monitor, Monitor is going to create a virtual monitor for you, and you'll be able to extend your monitor to that monitor that does not exist yet. That's a terrible user experience. So there's probably going to be a way to offer, like, as the first screen, do you want to extend the display or do you want to mirror the display? And when that happens, it's going to look a lot better and it's going to be easier to use. But this part is probably not going to be integrated in GNOME Shell, which is the desktop environment. And in the most remote future, it's possible that we implement a portal. Yes, remember the portals? That's such a far way off. It's going to take such a long time. Yes, yeah, remember the portals? It's possible that, like, in a few years from now, we make a portal for network displays. So applications can just ask, oh, can you show just my window on that projector there? So you would have like a screencasting button in your video player. And then you can share just the video player and you don't have to worry about the monitor and video and like which one is which and where's the cursor. But this is like in the far away future. But this work of separating GNOME network displays into its smallest and more modular components sort of lays the ground for this to happen in the future. And that's where we want to get. Screencasting portal. That's the end goal. So, yeah, so I think that's actually the end of the... Does anyone have any other question?
In cell phones, we have like divided display. You can like really use the first one, like YouTube and now. But is there any like you see in the future you get a TV and like, oh, I want to display my phone on the right side and my desktop in the left side, and I have like two monitors in the same TV, like virtualize the screen on the TV. Is that possible? Because it's just like instead of virtualize the window in the desktop, you virtualize the server side.
It is possible, we just need to implement that.
Look, I think there is a computer monitor that does that somehow. Like, it's an ultra-wide monitor, and it can pretend to be two monitors. So you could do that, but that would depend on the monitor. But if you want to do something like that today, you can use an Android emulator, drag the window to the side, drag the other window to the side, and then you can pretend it's another window, it's another monitor. I think that's the farthest you can get, like, this night. Without buying a new expensive weird television. It has like a far more thing for it.
You have to buy the adapter.
If your TV is not born smart, if you have a smart TV, then it probably has Miracast capabilities. Mine did not. She didn't. She wasn't born. So I had to buy the screencasting dongle, but it's like super cheap Chinese white label. You're gonna find like a 60 reais. Yeah, it's really cheap. Yeah, and some projector. Yeah, some smart TV projectors, dongle or Chromecast. What else?
Any other questions? Okay, thank you.
Guess that's it.
So we are going to the happy hour at Lado B. So if anyone wants to join us, you are welcome there. As I said before, you are on your own there. So we don't have sponsors for that. And tomorrow we have the welcome coffee at 9, without coffee probably, sorry about that. And at 9:30 we start with welcome session and then the rest of the talks. Thank you very much, folks.
Thank you.
Parabéns.